November 20th, 2025. New images have arrived from 3i Atlas, and they reveal details we did not anticipate. For weeks, telescopes and observatories around the world have tracked this object, monitoring its surface, its trajectory, and its emissions. But the latest data paints a picture that contradicts everything we believed we understood. What was once thought to be a routine observation now carries implications that ripple through every model of orbital behavior and celestial composition we rely on. The photographs show formations that do not align with prior structural analysis. Shadows fall where no ridges were expected. Reflectivity patterns suggest materials previously undetected, with spectral fingerprints that refuse to match known classifications. Even subtle deviations in its orbital path, measured across multiple observatories, hint at forces or influences we have yet to identify. Observers are now confronted with a scenario where the familiar is suddenly unfamiliar. The questions multiply. What is the true nature of this object? And what might these anomalies indicate about its origin or future behavior? Tonight we examine what these images reveal, why they matter, and what they might be hiding. And as one possibility fades, another emerges. We begin with the first of these new, unexpected surface irregularities. The first images that arrived on November 20th, 2025 show 3i Atlas in a way that challenges the assumptions we had built over weeks of observation. High-resolution imaging from multiple observatories has revealed surface features that appear inconsistent with previous models. Where earlier scans suggested a relatively smooth or uniformly pocked terrain, the new photographs depict formations that are irregular, sharply contoured, and unexpectedly complex. Measurements taken from stereoscopic imaging indicate subtle angular structures, ridge-like protrusions that do not correspond to natural impact crater patterns. Shadows cast by these formations imply height variations greater than those predicted by prior digital elevation maps, with some ridges rising nearly twice as high as the surrounding terrain. These differences, while minor in absolute terms, are significant because they disrupt our understanding of how this object has evolved in its orbital environment. Comparisons with prior imaging data highlight that many of these formations were either entirely undetected or misinterpreted due to resolution limits. It is not merely that the object is rougher than expected, the geometry itself is inconsistent with gradual erosion or standard impact processes. Some surfaces exhibit sharp, almost planar segments, while others slope gently into depressions that appear artificially regular, suggesting some process acting with precision beyond what typical micrometeorite impacts would produce. Spectral analysis of the surface compounds the mystery. Reflected light in specific bands highlights subtle differences in material composition across these ridges. Certain regions absorb and scatter light differently, indicating heterogeneous distribution of minerals or other elements across areas just a few meters apart. These variations were not observable in earlier datasets, and they may explain why initial models classified much of the surface as homogeneous regolith. Now, it is clear that what we once considered uniform is in fact a patchwork of differing reflective properties, densities, and textures. Furthermore, the ridges and irregular depressions appear oriented in ways that defy simplistic models of rotational stress. If 3i Atlas were a loosely consolidated body, we would expect patterns of stress fractures and erosion to form along predictable lines dictated by rotational dynamics. Instead, the formations appear organized in multiple directions, intersecting at angles inconsistent with known stress vectors. The implications are significant. Either the object's internal structure is more coherent and resistant than previously assumed, or some unknown external influence is shaping these surfaces. Detailed photometric analysis shows variations in albedo that suggest fine particulate layers overlying harder substrates. In certain depressions, light scattering indicates a reflective surface beneath a thin layer of granular material, possibly displaced by minor seismic or impact events. However, the distribution of these deposits is irregular. Some slopes are stripped almost completely of fine material, while adjacent areas retain layers with thicknesses measurable in tens of centimeters. This patchiness raises questions about the processes capable of selectively redistributing surface material across such small scales. Even more striking are areas where ridges intersect with previously documented craters. Rather than simple superposition, the formations suggest localized deformation, as if sections of the surface have shifted after impacts occurred. Analysis of crater rims and adjacent ridges shows subtle but detectable misalignments, implying either post-impact tectonics, internal shifting, or a combination of both. These interactions, barely perceptible in prior imaging, now form a network of structural anomalies that demand closer scrutiny. The spatial distribution of these irregularities also defies probability expectations. Statistical mapping indicates clustering of formations in patterns that are highly non-random. Certain quadrants exhibit a density of ridges and depressions several times higher than surrounding areas. While natural impact fields and erosion can create localized clustering, the consistency of alignment and repetition of shapes suggests an underlying mechanism that remains unexplained. Interestingly, the formations do not conform to expectations based on rotational exposure. One might assume that ridges and depressions form preferentially along equatorial or polar axes, reflecting the distribution of centrifugal forces. Yet the observed orientations appear nearly independent of rotational vectors, complicating any straightforward model of formation through spin-induced stress. Each ridge, depression, and protrusion seems to follow its own rule set, implying a process that is either stochastic in nature or influenced by forces beyond simple physics as currently understood. Thermal imaging adds another layer of complexity. Some ridges retain heat longer than surrounding terrain, while nearby depressions cool more rapidly. These microthermal variations suggest differences in material density or composition, with certain regions absorbing and retaining solar energy differently. The implication is that the surface is not only irregular geometrically, but also heterogeneous in thermal properties, which may affect rotational dynamics and surface stability over time. Comparative analysis with other small bodies in the solar system reveals that while irregular surfaces are common, the combination of sharp ridges, intersecting depressions, and heterogeneous composition on 3I Atlas is unusual. Most small bodies display either heavily cratered, randomly distributed surfaces or smoothly eroded regolith with minor anomalies. The newly observed complexity, particularly in light of previously uniform assumptions, elevates 3I Atlas into a category that defies easy classification. The anomalies observed on 3I Atlas's surface also raise questions about observational methodology. High-resolution imaging, now enhanced with adaptive optics and multispectral sensors, provides perspectives unattainable even a few months ago. This means that what we are observing is both a product of technological advancement and an actual evolution, or previously unobserved features of the object itself. Distinguishing between new formations and newly visible old formations is a critical challenge. Yet even with these considerations, the irregularities appear too precise and structured to be dismissed as observational artifact. The combination of geometric, spectral, thermal, and spatial irregularities presents a pattern that is difficult to reconcile with prior models. Each new dataset amplifies the strangeness of the surface. Ridges of varying height, depressions of inconsistent shape, and material heterogeneity that resist classification. Together, they form a puzzle where each piece defies the expected outcome, forcing observers to consider alternative processes, including the potential for internal structural differentiation or interactions with unknown forces in its immediate orbital environment. But these surface irregularities are only part of the story. While the formations themselves are striking, their presence has direct implications for the object's dynamics, including stability, rotation, and future evolution. Minor structural inconsistencies can amplify forces over time, potentially leading to subtle shifts in trajectory or surface rearrangements. This interconnection between visible anomalies and orbital behavior hints at a deeper complexity, one that will become increasingly relevant as additional data streams arrive. Yet one question remains unanswered. If these formations are natural, what processes could create such precise, heterogeneous, and intersecting structures on a small celestial body? And if they are influenced by external forces, what is the origin of that influence? As imaging continues and analyses deepen, these surface irregularities set the stage for the next layer of investigation. The spectral signatures that accompany them, revealing the materials, the anomalies revealed on 3I Atlas's surface are mirrored in its spectral readings, offering a window into the composition of the object in unprecedented detail. Over the past weeks, multiple observatories and space-based telescopes have captured high-resolution spectra across visible, infrared, and near-ultraviolet bands. The results are as perplexing as they are compelling. Where prior observations suggested a relatively homogeneous surface dominated by silicate-rich regolith, the new spectra reveal a complex mosaic of materials with variations that cannot be explained by standard asteroid or small body models. Initial analysis focused on the visible spectrum. Reflectance measurements across multiple wavelengths show abrupt changes in albedo over small spatial scales, consistent with the ridges and depressions mapped in the previous chapter. Some areas exhibit unusually high reflectivity, resembling freshly exposed material, while adjacent regions are significantly darker, suggesting either space weathering or compositional variation. Crucially, the reflectivity contrasts are sharper than expected for surface material exposed to constant micrometeorite bombardment over millions of years. This abrupt heterogeneity indicates that either 3I Atlas is dynamically resurfacing in ways not yet understood, or that it possesses inherent compositional layering from its formation. Infrared spectra add a second layer of complexity. Observations in thermal infrared bands indicate absorption features associated with silicates, but their intensity and distribution are inconsistent. Certain regions exhibit absorption peaks corresponding to olivine and pyroxene, yet other neighbouring regions appear to contain elements that resemble metallic iron or even more exotic compounds rarely observed in small bodies. These materials are unevenly distributed, creating a patchwork that challenges the assumption of a single, cohesive mineralogical identity. The scale of these variations, occurring across tens of meters, is remarkable. Even high-resolution Earth-based radar and spacecraft imaging rarely resolve compositional changes at this level without direct sampling. Spectral line shifts further complicate the picture. Precise Doppler measurements of emitted or reflected light show small but measurable deviations from expected values, suggesting subtle changes in the velocity of surface layers. While these shifts are minor, they are consistent across multiple observation platforms, ruling out instrumentation error. The implication is that either the surface is actively moving through micrometeoroid-induced regolith shifts, thermal contraction, or an unknown mechanism, or that the spectral properties themselves are altered by structural or electromagnetic effects that influence light absorption and emission. Near-ultraviolet data is particularly revealing. Several regions exhibit anomalous absorption bands that do not match known compounds commonly found in asteroids or minor planets. These features could indicate the presence of carbon-rich organics, exotic oxides, or other rare compounds. Although the exact nature of these materials remains uncertain, their distribution aligns with certain ridges and depressions mapped in previous imaging. This correlation suggests a link between morphology and composition, hinting that the unusual surface geometry is not merely a physical anomaly, but may be chemically or structurally significant. One striking observation is the contrast between areas exposed to direct solar radiation and those in shadow. Thermal gradients do not fully explain the differences in spectral absorption, implying that material composition itself varies independently of sunlight exposure. This suggests a heterogeneous surface layer that has either preserved ancient material beneath transient debris or undergone processes that selectively expose or conceal certain compounds. The result is a patchwork spectrum, challenging any attempt to model 3I Atlas as a monolithic body. Spectral ratios between different bands also raise questions about grain size and surface roughness. Certain high reflectance regions display ratios consistent with fine, smooth regolith, while neighbouring depressions exhibit absorption patterns typical of coarser, rougher material. These variations imply active segregation of particulate matter across the surface. Unlike larger bodies, where gravity dominates particle movement, the small scale of 3I Atlas would typically limit such differentiation. Yet the observed segregation is clear, suggesting an internal or external mechanism capable of selectively transporting or exposing specific materials. Additionally, polarimetric data adds nuance to the spectral analysis. Measurements of light polarization reveal variations in surface texture and scattering properties that correspond to compositional anomalies. Regions exhibiting higher degrees of polarization align with ridges, whereas low polarization areas correspond to smoother or darker surfaces. This reinforces the observation that morphology and composition are intertwined, and that the irregular surface forms mapped earlier are not superficial but intimately connected with the object's material properties. comparison with meteorite analogues provides partial context but leaves gaps. While some spectral features resemble ordinary chondrites, the presence of unusual absorption bands and inconsistent thermal behavior suggests materials either not represented in our meteorite collections or significantly altered by processes in space. This raises the possibility that 3I Atlas may contain components formed under conditions unlike those experienced by typical asteroidal bodies, whether through unique early solar system processes, collisions, or other phenomena not yet documented. Further, spectral monitoring over time reveals subtle temporal variations. Observations over several days indicate minor changes in reflectivity in certain regions, particularly those near sharp ridges or exposed slopes. While small, these variations are statistically significant and repeatable across multiple telescopes. The causes could include micrometeorite impacts, thermal cycling, or electrostatic dust movement, phenomena that are difficult to quantify remotely but may be active on 3I Atlas. These fluctuations hint at a dynamic surface, even in the absence of a significant atmosphere or internal activity, suggesting that the object may be more active than previously believed. Spectral anomalies also correspond with previously recorded orbital deviations. Certain high reflectance or low reflectance areas are associated with regions of the object where minute shifts in trajectory were noted. While correlation does not confirm causation, this spatial relationship suggests that surface composition may influence the distribution of mass or structural rigidity, in turn affecting rotation or orbital stability. Understanding this connection is critical, as it could reveal mechanisms that impact not only 3I Atlas, but similar small bodies in unpredictable ways. Taken together, these spectral observations indicate a surface that is compositionally complex, morphologically irregular, and dynamically responsive. What appears at first glance as a single celestial body is, in fact, a mosaic of materials, textures, and processes. The anomalies are not isolated. They interconnect, reinforcing patterns that were first hinted at in the imaging data and setting the stage for deeper investigation. The spectral heterogeneity forces a re-evaluation of prior assumptions. Standard models that categorize small bodies based on average reflectivity or dominant mineral composition are insufficient. 3. I-Atlas resists simplification, displaying signatures of multiple materials layered across fine spatial scales, suggesting either unusual formation, subsequent modification, or both. The variability in spectral lines, polarimetric data, and thermal correlations together indicate that 3I Atlas is not only structurally complex but also chemically intricate. Yet questions remain. How did these compositional variations arise, and why do they correlate so closely with surface morphology? Are they remnants of the object's formation, or products of processes occurring in its current orbital environment? Do they influence, or are they influenced by, its observed orbital deviations? Each answer opens new avenues of investigation, pointing toward mechanisms that could range from entirely natural processes to interactions that are as yet unidentified. As one possibility fades, another emerges. If the spectral anomalies are indicative of exotic materials or internal differentiation, then 3I Atlas may be far more structurally and chemically sophisticated than any small body previously catalogued. Its surface, previously assumed to be a simple regolith, may instead represent the external expression of complex internal processes. And if this is the case, every subsequent observation, from thermal behavior to electromagnetic readings, must be reconsidered in light of this newfound complexity. The spectral data also underscores the importance of multi-wavelength monitoring. Observations across visible, infrared, and near-ultraviolet bands reveal layers of information invisible in single spectrum analysis. Only by integrating these perspectives can a coherent, if provisional, understanding emerge. And as we begin to correlate these spectral signatures with surface structures, thermal anomalies, and orbital deviations, the full picture of 3I Atlas starts to take shape, but it is a picture that is far from complete. The next step is to examine how these compositional patterns relate to the object's movement through space. The orbit of 3I Atlas has exhibited subtle deviations, and understanding whether surface material distribution influences its trajectory or whether external forces interact with its heterogeneous composition is critical. Spectral evidence, after all, may hold clues not only to the object's material identity, but also to the mechanisms driving its present behaviour and its potential evolution. As the surface irregularities and spectral anomalies of 3I Atlas became clear, another question emerged. What do these features mean for the object's motion through space? For months, astronomers have tracked 3I Atlas with high-precision instruments, creating models that predict its trajectory with remarkable accuracy. Until recently, its orbit appeared stable, adhering closely to the parameters derived from gravitational calculations and minor perturbations from nearby bodies. However, the latest datasets captured over the past several weeks indicate subtle but persistent deviations, shifts that, while small, cannot be ignored. The first evidence of orbital drift came from coordinated measurements by ground-based observatories and space telescopes. Observers noted a tiny discrepancy between the predicted and observed position of 3I Atlas, amounting to a few hundred meters over a span of several days. At first glance, such a deviation could have been dismissed as a minor error in measurement. Yet repeated observations confirm the discrepancy, and the drift appears consistent rather than random, suggesting that it is real and requires explanation. Detailed modelling reveals that these deviations are not uniform along the orbit. Certain segments exhibit greater positional variance than others, hinting at influences beyond simple gravitational perturbations. If 3I Atlas were a uniform, rigid body, its trajectory should respond predictably to the combined gravitational forces of nearby planets, the Sun and other minor bodies. The observed variations suggest either an uneven distribution of mass within the object, or subtle forces acting externally, or a combination of both. The surface anomalies documented in earlier chapters may provide part of the answer. High-density ridges, depressions, and heterogeneous materials can create uneven mass distribution, subtly shifting the centre of mass. In turn, this can affect rotational dynamics, leading to precession or wobble that slightly alters the orbital path. While such effects are minuscule in absolute terms, over the course of weeks or months they accumulate, producing measurable deviations from predicted positions. Electromagnetic interactions may also contribute. Observations of fluctuating electromagnetic fields around 3I Atlas suggest that its movement through the solar wind could generate forces capable of nudging its trajectory. The intensity of these interactions appears to correlate with certain surface regions identified in spectral analyses, implying a connection between composition and orbital behaviour. Highly conductive areas, or regions with unusual charge retention properties, may interact differently with charged particles in space, producing asymmetric forces. Thermal effects too play a subtle but significant role. The Yarkovsky effect, long documented in small solar system bodies, causes objects to slowly drift due to anisotropic thermal emission. On 3I Atlas, the thermal heterogeneity observed in infrared imaging, hot ridges, cooler depressions, irregular surface albedo, could amplify this effect in unexpected ways. Rather than producing smooth, predictable drift, the variable emission patterns could introduce localized accelerations, further complicating orbit prediction. Temporal analysis of the orbital drift shows patterns that align with rotational cycles. Certain positions in the orbit correlate with slight accelerations or decelerations along the expected path. This connection reinforces the notion that surface features, coupled with rotation, may be influencing the trajectory through thermal and radiative effects. The relationship is subtle but measurable, suggesting that 3I Atlas cannot be treated as a simple point mass when modelling its movement. Interestingly, orbital deviations also show correlation with recent imaging events. Areas of high surface complexity, clusters of ridges, intersecting depressions and material heterogeneity appear to coincide with segments of the orbit where positional drift is most pronounced. While causation cannot be confirmed, the correlation raises important questions about the interaction between physical structure and orbital stability. If mass is unevenly distributed across these formations, it could create torque or induce minor shifts in angular momentum, translating into trajectory changes over time. Another layer of complexity arises when considering gravitational interactions with nearby minor bodies and solar radiation pressure. While these factors are typically small, they are amplified in an object with a heterogeneous surface and a regular shape. The combination of uneven mass, electromagnetic interactions, and thermal effects produces a multidimensional system in which predicting precise motion becomes increasingly difficult. Even minor miscalculations in mass distribution or surface properties can lead to observable drift over relatively short timeframes. Recent simulations that incorporate detailed topographical and compositional data provide further insight. Models that treat 3I Atlas as a uniform body fail to account for observed deviations. By integrating heterogeneity in density, surface conductivity, and thermal emission, simulated trajectories better align with actual measurements. These simulations, however, remain provisional, as uncertainties persist regarding the exact distribution of materials and the impact of dynamic processes such as micro-impacts, surface shedding, or electrostatic dust movement. The orbital drift is not merely a technical curiosity. It carries implications for understanding 3I Atlas's long-term evolution. Even minor deviations can compound over months and years, altering close approaches, potential collision risk with other minor bodies, and observational planning. For scientists tracking the object, accounting for these shifts is essential to maintaining predictive accuracy and understanding the forces at play. The subtle deviations may also hint at underlying processes that affect small bodies more generally, offering a rare opportunity to study complex interactions between surface heterogeneity and orbital mechanics. One particularly puzzling aspect is the persistence of drift even during intervals when external influences should be minimal. During periods of reduced solar activity and limited gravitational perturbations, the deviations continue, suggesting internal factors may be at play. Internal density variations, structural shifts, or even unexplained micromotions within the object could be contributing. These possibilities raise the stakes, as they imply that 3I Atlas may possess dynamic properties previously unrecognized in small, seemingly inert bodies. The interplay between surface features and orbital dynamics also has broader scientific implications. If the ridge depression structures and heterogeneous composition directly influence motion, it challenges conventional methods of treating minor bodies as homogeneous, inert objects in orbital modeling. 3. I Atlas may represent a class of objects whose structural complexity fundamentally affects their trajectories, requiring new frameworks for prediction and analysis. Yet even as scientists refine their models, the underlying cause of the drift remains an open question. Is 3I Atlas's orbital behavior simply the sum of measurable physical effects, uneven mass, thermal emission, electromagnetic interactions, or is there an additional, currently unrecognized force at work? Each observation, each spectral reading, and each imaging dataset adds a piece to the puzzle, but the overall picture remains incomplete. The orbital deviations also influence how new observations are planned. Telescopes must adjust tracking parameters more frequently to compensate for unexpected shifts, complicating high-resolution imaging campaigns. In turn, this affects the ability to monitor surface evolution, thermal anomalies, and electromagnetic fluctuations, creating a feedback loop where each element, surface, composition, orbit, interacts with the others in ways that must be carefully untangled. Finally, the orbital drift underscores a fundamental truth. 3I Atlas is not a passive object. Its surface, internal structure, and environment are interconnected in ways that actively shape its motion through space. What was once considered a relatively straightforward observational target is now revealed to be a complex evolving system, challenging our understanding of small body dynamics. Each ridge, each depression, each compositional anomaly contributes not only to the surface complexity, but also to the subtleties of its path through the solar system. As we move forward, the next layer of investigation must integrate high-resolution imaging, spectral data, and thermal readings to understand the forces driving these deviations. The orbit cannot be separated from the body itself. The two are intrinsically linked. And as one possibility fades, another emerges. If internal structure or unknown interactions are influencing trajectory, then every observation, from ridges to spectral lines to thermal anomalies, becomes a critical piece in predicting 3I Atlas's future path and understanding the forces shaping it today. The arrival of high-resolution images on November 20th, 2025, offered an unprecedented view of 3I Atlas, revealing details that earlier datasets had only hinted at. Unlike prior observations, which relied on moderate resolution optics and partial spectral imaging, these new images resolve structures on scales of a few meters, providing an extraordinary window into the object's surface geometry, material distribution, and possible internal processes. The images, captured from both space-based and ground-based observatories, confirm some of the anomalies suggested by earlier datasets, while simultaneously introducing entirely new questions. The first striking aspect of the high-resolution imagery is the intricate network of ridges, depressions, and protrusions across the surface. Whereas low-resolution imaging suggested general roughness, the fine detail now shows complexity in 3 dimensions. Individual ridges display sharp edges and subtle curvature, some running for tens of meters with surprisingly uniform slopes, while others intersect at seemingly improbable angles. Shadows in the images, measured against known solar angles, reveal elevations that challenge prior digital elevation models, with certain peaks exceeding earlier height estimates by as much as 50%. Closer examination of depressions shows an array of unexpected features. Some appear to be impact craters, though their rims and interiors differ from conventional expectations. Crater walls are irregular, sometimes exhibiting internal ridges and secondary depressions that hint at structural heterogeneity beneath the surface. Others show signs of slumping or partial collapse, suggesting minor internal movement or shifting of material over time. The juxtaposition of stable ridges and deformable depressions raises immediate questions about the internal composition and structural cohesion of 3I Atlas. Material heterogeneity is apparent even at this scale. Some ridges are smoother and more reflective, while adjacent slopes are darker and rougher. Spectral overlays indicate that these variations correspond to compositional differences detected in previous chapters, confirming that what might appear uniform at low resolution is, in fact, a mosaic of distinct materials. The juxtaposition of light and dark areas is not random. High reflectance ridges often coincide with areas of increased structural integrity, while darker zones correlate with surface depressions and weaker material. Perhaps most intriguing are the patterns of alignment and repetition across the surface. Certain ridges appear in parallel formations separated by consistent intervals, while other depressions cluster in repeating motifs. This level of geometric regularity is unusual for small celestial bodies and does not conform neatly to impact cratering or random erosion models. The possibility that these formations result from unknown internal processes or subtle external influences cannot be dismissed. The alignment of these features may offer clues about stress patterns, rotational effects, or other forces acting upon 3I Atlas. High-resolution imaging also reveals microtextures that were invisible in previous observations. Fine grooves and striations run across certain ridges, suggesting minor surface movement, abrasion, or possibly electrostatic dust migration. In depressions, small accumulations of reflective material hint at selective deposition, possibly influenced by microgravity, thermal cycling, or even electromagnetic effects. These microtextures not only indicate ongoing surface processes, but also provide context for understanding larger-scale anomalies in morphology, composition, and orbital dynamics. Shadow analysis, combined with precise measurements of solar angles at the time of imaging, enables calculation of surface slopes, ridge heights, and depression depths with unprecedented accuracy. Certain ridges, particularly those oriented perpendicular to the primary axis of rotation, display height-to-width ratios that defy expectations based on small body formation models. Their persistence and sharpness suggest that either the material composing these structures is unusually cohesive, or that external forces have contributed to their maintenance. This observation aligns with spectral data indicating denser or more rigid materials concentrated in elevated regions. An unexpected discovery in the high-resolution images is the presence of small-scale disruptions and fractures along several ridges. These fractures do not appear to result from impact events, but rather from internal stress or gradual thermal expansion and contraction. The pattern of these microfractures is non-uniform, occurring predominantly in ridges that coincide with heterogeneous composition zones identified through spectral analysis. This correlation reinforces the emerging hypothesis that 3I Atlas is internally complex, with surface expressions reflecting subsurface structural variations. Imaging also confirms the presence of subtle surface depressions that may function as microtraps for particulate matter. Fine regolith appears to accumulate in these depressions, often contrasting sharply with adjacent ridges that remain largely free of loose material. observations over several days indicate that some particulate deposits may shift slightly, implying dynamic processes at work, potentially influenced by thermal cycling, rotational motion, or minor impacts. Even small movements, imperceptible in prior datasets, now become significant when correlated with spectral and orbital anomalies. One particularly notable feature revealed in high-resolution imagery is a series of small planar surfaces embedded within larger ridges. These surfaces are unusually flat and exhibit reflectivity distinct from surrounding material. Their origin is unclear. They could represent remnants of older formations, exposure of denser subsurface material, or effects of external forces acting selectively on the surface. Whatever the explanation, their presence reinforces the conclusion that 3i Atlas is far more structurally complex than previously assumed. Edge detection and digital elevation mapping applied to the images provide additional insight. Certain ridges terminate abruptly, while others curve gently, suggesting differences in material cohesion, stress distribution, or both. Depressions are often irregularly shaped, with walls that slope asymmetrically, challenging simple gravity-based models of formation. The overall impression is of a surface shaped by multiple interacting processes, some likely internal, others environmental, with varying intensities across different regions. High-resolution imaging also allows for temporal comparison, albeit over a short interval. Images captured a few days apart show subtle changes in the appearance of certain micro-depressions and particulate accumulations. While these changes are minor, they confirm that 3i Atlas is not static. Its surface exhibits measurable dynamics even without major impacts. The rate and pattern of these changes may hold clues to ongoing processes, whether driven by microgravity, thermal cycling, or interactions with the surrounding space environment. Beyond the structural and compositional insights, the high-resolution images carry implications for understanding 3i Atlas's rotational behavior. The orientation of ridges and depressions relative to the rotational axis suggests that the surface experiences differential stress, potentially affecting spin rate or axis stability over time. Correlating these surface features with observed orbital drift strengthens the emerging picture of a body whose surface morphology, composition, and motion are interconnected in ways previously underestimated. The imagery also reinforces the limitations of prior observational methods. Lower resolution data, while valuable for general mapping, could not resolve the intricate network of ridges, depressions, and microtextures now visible. Without high-resolution images, the heterogeneity of 3i Atlas would have remained largely undetected, and critical correlations between morphology, composition, and dynamics would have been obscured. This demonstrates the importance of multi-scale observation, where fine detail complements broader spectral and orbital data. Taken together, the high-resolution images confirm and expand upon the anomalies identified in previous chapters. The surface is irregular, structurally complex, and compositionally heterogeneous. Patterns of ridges, depressions, and microtextures suggest ongoing processes that may include thermal cycling, electrostatic movement, or subtle internal shifts. These features correlate with spectral variations, electromagnetic anomalies, and minor orbital deviations, reinforcing the interconnected nature of the object's behavior. Yet, as with prior datasets, the images raise further questions. What mechanisms maintain the sharp ridges over time? How do small-scale surface changes influence the larger-scale morphology and orbit? Are the planar surfaces embedded in ridges remnants of internal processes, or evidence of external influences acting selectively? Each observation adds clarity to one aspect of 3i Atlas while revealing new layers of mystery in another. High-resolution imaging, therefore, is not merely a tool for visualization. It is a lens through which the object's dynamic and structural complexity becomes measurable, analyzable, and critically interpretable. Every ridge, depression, and reflective patch carries information about composition, stress, and environmental interaction. The images serve as both evidence and guide, pointing the way toward deeper investigations in subsequent chapters, including electromagnetic anomalies, thermal behavior, and internal structure. As one possibility fades, another emerges. The intricate surface captured in these images is both a record of past processes and a clue to ongoing phenomena, potentially influencing 3i Atlas's orbit, thermal patterns, and even internal stability. Understanding these features is essential before attempting to interpret broader behaviors, and the next step lies in examining the unexpected electromagnetic anomalies detected around the object, which may interact with the very structures revealed in these images. Alongside the detailed surface and compositional analysis of 3I Atlas, electromagnetic observations have revealed a further layer of complexity, one that challenges conventional expectations for small celestial bodies. Instruments designed to detect charged particle interactions, magnetic fields, and induced currents have recorded fluctuations that are both subtle and persistent. These variations, measured across multiple observational platforms, appear to correlate with surface irregularities and material heterogeneity, suggesting an intimate connection between morphology, composition, and electromagnetic behavior. Initial detection of electromagnetic anomalies came from radio and magnetometric surveys conducted in early November 2025. Observatories noted weak but consistent oscillations in the local magnetic environment surrounding 3I Atlas, exceeding background noise levels and persisting over multiple observation cycles. While small, these oscillations are significant because they cannot be easily explained by solar wind alone or by the body's interaction with ambient interplanetary magnetic fields. The anomalies suggest that 3I Atlas either contains conductive materials capable of generating local magnetic effects, or that external charged particles are interacting with surface structures in unusual ways. Detailed measurements indicate that these electromagnetic fluctuations are not uniform. Certain regions of the object exhibit stronger activity, particularly those corresponding to high-density ridges and sharp surface protrusions identified in high-resolution imaging. Conversely, smoother depressions show minimal fluctuation. This spatial correlation reinforces the hypothesis that surface morphology influences electromagnetic behavior, either by concentrating currents, guiding charged particle flow, or affecting localized magnetic induction. Polarimetric and spectral overlays strengthen this connection. Areas exhibiting anomalous electromagnetic activity often align with regions of high reflectivity or unusual composition, particularly metallic or conductive materials. These observations suggest that 3I Atlas is not a uniform insulator, but contains patches of material capable of interacting with ambient fields, producing detectable electromagnetic effects. The irregular distribution of these materials, combined with the intricate surface topography, may create localized microfields that influence particle movement and potentially thermal or structural behavior. High-frequency measurements reveal additional subtleties. Oscillatory patterns in the electromagnetic spectrum suggest that the object may generate or modulate currents in response to solar wind variations or rotational dynamics. Although the amplitudes are small, the regularity and persistence indicate a systemic property rather than random noise. The frequency spectrum shows peaks at intervals consistent with the body's rotation period, implying that some interaction between rotational motion and surface conductivity may be producing measurable effects. Furthermore, these fluctuations exhibit directional dependence. Magnetic vector analyses demonstrate that certain ridges and planar surfaces channel fields along preferred axes, amplifying localized interactions. These patterns are most pronounced along elevated ridges that correspond to highly reflective, compositionally dense areas. The combined effect of surface morphology, material heterogeneity, and rotational motion appears to create a network of electromagnetic activity that varies predictably across the object's surface. Electrostatic effects may also play a role. Observations suggest that charged dust particles on 3I Atlas's surface could be influenced by these electromagnetic microfields, producing small-scale particle migration. High reflectance ridges often appear free of fine regolith, while adjacent depressions accumulate material, a pattern consistent with electrostatic sorting. The magnitude of these forces is small but, over time, sufficient to redistribute surface material, subtly altering morphology, and potentially the reflective and spectral properties detected in prior observations. One notable implication of these findings is their potential influence on orbital and rotational behavior. While electromagnetic forces are typically negligible for small bodies in space, localized concentrations of conductive material interacting with charged particles could produce minor torques. When combined with thermal variations, uneven mass distribution and rotation, these electromagnetic effects may contribute to the subtle orbital deviations documented in previous chapters. Even if these forces are minuscule, their consistency and alignment with specific surface structures warrant careful consideration. Comparisons with other minor bodies show that 3I Atlas's electromagnetic activity is unusual. While small objects can generate weak fields, the combination of persistent oscillations, rotational modulation, and surface correlation sets it apart. Unlike asteroids with uniform surfaces or homogeneous material distributions, the complex surface and composition of 3I Atlas amplify and channel electromagnetic effects in ways rarely observed. This raises the possibility that the object represents a class of small bodies where morphology, composition, and electromagnetic interaction are intrinsically linked. Temporal analysis adds another layer of complexity. Over consecutive observational periods, the intensity and pattern of electromagnetic fluctuations exhibit minor but measurable changes. These variations are not random. They correlate with rotational position and exposure to solar radiation, suggesting dynamic interaction rather than static properties. Certain ridges appear to activate as they rotate into sunlight, while others remain largely inert, implying a coupling between surface heating, material conductivity, and electromagnetic response. Modeling these interactions presents challenges. Simulations incorporating known conductive materials, rotation, and solar wind conditions replicate some observed features, but fail to capture the full amplitude and spatial complexity of the fluctuations. This discrepancy indicates that unknown factors, possibly related to material composition, subsurface structure, or external influences, may be contributing. The electromagnetic anomalies cannot be fully understood in isolation. They must be interpreted in conjunction with morphology, spectral composition, and thermal behavior. The implications extend beyond surface processes. Persistent localized electromagnetic fields could influence dust charging, particle aggregation, or even minor microfractures within the ridges themselves. Observed surface fractures and slumping patterns may, in part, result from repeated electrostatic stress, especially in regions where ridges concentrate fields. Over time, these interactions could subtly reshape the surface, perpetuating cycles of structural change and material redistribution that reinforce the patterns identified in imaging and spectral analysis. Importantly, the electromagnetic anomalies also intersect with potential observational biases. Certain detection methods, particularly ground-based radio surveys, are sensitive to field directionality and local surface effects. The highly structured microfields on 3I Atlas could amplify or attenuate signals depending on the observer's orientation, leading to apparent inconsistencies in earlier data sets. Understanding the spatial and temporal distribution of these fields is therefore essential for accurate interpretation of both imaging and spectral measurements. Taken together, the electromagnetic fluctuations represent a critical component of 3I Atlas's ongoing mystery. They connect surface morphology, compositional heterogeneity, and dynamic behavior, suggesting that the object is not a passive, inert body, but an active system in which multiple processes interact. Ridges, depressions, planar surfaces, and spectral anomalies all appear to influence and be influenced by electromagnetic activity. This interplay hints at mechanisms that extend beyond traditional models of small body physics. Yet questions remain. What is the precise composition responsible for these conductive effects? How do microfields interact with surface regolith and larger-scale structures? Could electromagnetic processes contribute meaningfully to observed orbital deviations, or are they largely a surface phenomenon? Each observation provides a clue, but the full implications are only beginning to emerge. As one possibility fades, another emerges. The interplay of morphology, composition, rotation, and electromagnetic activity suggests a highly integrated system. The surface features that initially appeared anomalous in imaging and spectral analysis may, in fact, be active participants in processes that shape 3I Atlas's evolution. Understanding these fluctuations is essential not only for interpreting current observations, but also for predicting future behavior, particularly as we integrate data on thermal anomalies, internal composition, and orbital dynamics. The next step is to examine thermal signatures in detail, assessing how heat retention, cooling patterns, and surface material interactions may interact with both morphology and electromagnetic fluctuations to influence the object's behavior. Only by integrating these layers surface, composition, electromagnetic activity, and thermal dynamics, can a coherent understanding of three-eye atlas begin to emerge. Thermal analysis has emerged as one of the most revealing tools for understanding three-eye atlas, uncovering patterns of heat retention, emission, and fluctuation that correlate with surface morphology, composition, and electromagnetic anomalies. Observations conducted over the past weeks, using both ground-based infrared telescopes and spaceborne thermal instruments, provide unprecedented insight into how this object responds to solar radiation and internal processes, offering clues about its material properties and dynamic behavior. The initial data confirm that three-eye atlas does not behave like a simple, homogeneous body. Temperature measurements across different surface regions show variations far greater than expected for an object of its size and distance from the Sun. Elevated ridges, previously noted in high-resolution imagery, retain heat longer than surrounding depressions, while some lower areas cool more rapidly once shaded. The differences, measurable in several degrees Kelvin over the course of a single rotation, indicate that material composition, surface geometry, and thermal inertia interact in complex ways. Infrared spectral overlays correlate these thermal variations with the compositional heterogeneity identified in prior chapters. Reflective, high-density ridges, often composed of metallic or highly conductive materials, absorb and release solar energy differently from darker, less dense regions. This differential heating likely contributes to localized stress along surface ridges and depressions, potentially influencing microfractures, regolith migration, and even the electromagnetic anomalies documented in previous observations. In effect, heat distribution on three-eye atlas is not uniform. It is structured, reflecting the underlying heterogeneity of the object itself. One of the most striking findings is the persistence of thermal hotspots. Certain elevated regions, particularly planar surfaces embedded within ridges, remain warmer than their surroundings even after prolonged periods without direct sunlight. These anomalies suggest that the materials in these regions have unusually high heat retention, possibly indicating dense metallic components or that subsurface structures are influencing thermal conduction. The presence of such hotspots implies that three-eye atlas is not only chemically complex, but thermally active on a microscale, with localized energy reservoirs that could subtly affect surface morphology over time. Thermal gradients across slopes and depressions provide additional insight into regolith movement and surface stability. Fine particulate matter tends to accumulate in cooler depressions, while heated ridges appear to shed loose material. This pattern, visible in repeated thermal imaging over consecutive days, aligns with observations of dust redistribution and electrostatic particle movement. Heat, in combination with localized electromagnetic effects, seems to drive minor but measurable surface dynamics, reshaping the object incrementally and possibly influencing its reflective properties and spectral signatures. Temperature variations also affect rotational dynamics. Differential heating across the surface can create micro-torques, particularly on elongated ridges or unevenly distributed material. These torques are minuscule, yet consistent, and may contribute to the slight wobble observed in the rotation axis, which correlates with orbital drift anomalies. Thermal forces, acting in conjunction with irregular mass distribution, electromagnetic fluctuations, and surface morphology, form an integrated system in which energy absorption and emission have direct implications for both structural stability and motion. Another layer of complexity arises from diurnal and orbital cycles. As three-eye atlas rotates, regions exposed to sunlight experience rapid heating, followed by slower cooling in shadow. Thermal inertia varies across the surface, with denser, more reflective areas responding more slowly to changes in solar input. These variations produce subtle but measurable asymmetries in heat distribution, amplifying the effects of ridges and depressions while influencing local surface stress patterns. Over time, such thermal cycling could induce microfractures, material fatigue, or minor shifts in surface regolith, contributing to ongoing morphological evolution. The combination of surface geometry and thermal behavior also affects electromagnetic activity. Areas that remain warmer longer, particularly ridges with high conductivity, may generate localized currents through thermoelectric effects or enhanced interaction with the solar wind. Observational correlations indicate that thermal anomalies align with regions of electromagnetic fluctuation, suggesting an interdependent system in which heat, surface composition, and electrical properties reinforce one another. This interplay may explain some of the persistent but previously unexplained anomalies observed in multiple datasets. Thermal imaging has further revealed subtle variations in albedo and reflectivity linked to heating patterns. Some high reflectance ridges show a slight shift in apparent brightness over the course of a rotation, likely due to temperature-induced changes in surface properties. These observations reinforce the idea that 3I Atlas's surface is dynamic, not static, with energy absorption and emission processes actively altering optical characteristics on timescales as short as hours. Such dynamic behaviour is rare among small bodies and underscores the object's unusual physical and chemical complexity. Modelling the thermal behaviour of 3I Atlas requires integrating multiple factors: material composition, surface morphology, rotation, solar angle, and localised electromagnetic effects. Simulations that attempt to treat the object as uniform fail to reproduce the observed heat distribution, highlighting the importance of incorporating heterogeneity and microscale dynamics. Models that do include compositional and morphological complexity come closer to matching the data, yet discrepancies remain, particularly in regions with planar surfaces or anomalous ridges. These areas appear to retain or dissipate heat in ways that defy current predictive models, indicating that unknown internal or external factors may be at work. The implications of thermal behaviour extend beyond surface processes. Localised heating and cooling can induce microstresses in ridges and depressions, potentially driving minor shifts or slumping events. Thermal cycles may also influence orbital dynamics through subtle torque effects, particularly when combined with uneven mass distribution and rotation. In essence, heat is not merely a passive property of 3I Atlas. It is an active agent influencing both structure and motion. Temporal analysis reveals additional surprises. Short-term thermal fluctuations measured over intervals of hours indicate that some regions respond more rapidly than expected to changes in solar exposure. Conversely, other areas exhibit delayed thermal response, suggesting subsurface conduction or hidden structural complexity. These differences imply that beneath the observable surface lies a network of materials and microstructures capable of modulating heat flow in ways that remain difficult to quantify remotely. Understanding these hidden features is essential for predicting both surface evolution and broader dynamic behaviour. Finally, thermal analysis emphasises the interconnected nature of the object's anomalies. Ridges, depressions, material heterogeneity, electromagnetic fluctuations, and orbital drift all interact with heat in ways that reinforce and amplify each other. The surface features captured in high-resolution imagery are not merely static. They are actively involved in processes that influence morphology, composition, and motion. Each thermal cycle carries the potential to alter microstructures, redistribute particles, and even contribute to subtle rotational and orbital changes. Yet critical questions remain. How deep do these thermal variations penetrate beneath the surface, and what does this imply about internal composition? To what extent do thermal cycles contribute to the observed orbital drift? Are microscale heating effects sufficient to explain persistent surface changes, or do they act in concert with electromagnetic, structural, or external influences? Each observation adds to the puzzle, but the complete picture of 3I Atlas remains elusive. As one possibility fades, another emerges. Heat is not just an observable property, it is a driver of ongoing surface evolution, interacting with material heterogeneity, electromagnetic activity, and structural anomalies. Understanding thermal behaviour is essential to decoding the object's morphology, predicting minor movements, and anticipating the ways in which 3I Atlas may continue to evolve over time. The next layer of investigation must look inward, toward internal composition and structural integrity, to assess how these factors relate to the surface and to the complex interactions already documented. Beyond the surface, thermal anomalies, electromagnetic fluctuations, and orbital deviations hint at a deeper layer of complexity, the internal structure of 3I Atlas. Until recently, small bodies of this size were assumed to be loosely consolidated or monolithic, their interiors largely uniform or dominated by rubble piles. Yet the cumulative evidence, surface ridges, compositional heterogeneity, microfractures, and thermal behaviour suggest that 3i Atlas may harbour internal structures far more intricate than previously imagined. Seismic analogues, though indirect, offer the first clues. Observations of subtle surface vibrations likely induced by micrometeoroid impacts, thermal cycling and rotational forces provide insight into how energy propagates through the body. The patterns of vibration, inferred from high-resolution imaging and high-frequency spectral analysis, suggest that some regions transmit energy differently than others. Dense ridges and planar surfaces appear to channel vibrations efficiently, while surrounding depressions dissipate them rapidly. Such differences are consistent with internal layering, variable material density, or even embedded structures that alter the propagation of mechanical energy. Gravitational mapping, derived from orbital perturbations and precise tracking of motion, reinforces this view. The orbital drift and rotational wobble, observed in previous chapters, cannot be explained solely by surface features. Modelling indicates that mass distribution within 3i Atlas is uneven, with higher density cores aligned with some of the prominent surface ridges. Conversely, regions with extensive depressions and low reflectance material appear to be underlain by less dense or more porous material. These findings imply that the internal architecture is stratified, with distinct zones of varying density and rigidity, challenging the notion of uniformity in small bodies. Internal thermal modelling further supports the presence of layered structure. Heat retention in certain planar ridges and elevated regions exceeds what would be expected from simple surface composition differences alone. The persistence of hotspots indicates subsurface materials with higher thermal conductivity, likely denser or more metallic, capable of storing and redistributing heat. This suggests that beneath the observable regolith lies a complex interior capable of moderating thermal energy, possibly including solid cores, embedded slabs, or compacted layers that differ from the surrounding matrix. Electromagnetic observations intersect with internal structure as well. Conductive materials on the surface, aligned with ridges and planar formations, likely extend into subsurface layers. These materials can create localized magnetic or electrostatic fields, as evidenced by the anomalies detected in Chapter 5. The spatial correlation between surface conductivity, thermal retention, and electromagnetic fluctuation implies that internal structures are not passive. They actively influence observable properties and may respond dynamically to external forces, including solar wind and thermal cycling. Subsurface fractures and stress zones are also inferred from the combined datasets. Microfractures on the surface align with regions of anomalous thermal stress, suggesting that underlying material heterogeneity amplifies or directs stress propagation. These fractures may serve as conduits for internal material movement, or as weak points along which the body could slowly adjust or deform over time. Such structural complexity challenges simple models of small body mechanics and indicates that 3i Atlas is more resilient and internally intricate than its size might suggest. The ridge depression network observed on the surface also offers indirect insight into internal composition. Sharp, elongated ridges may correspond to internally supported structures, possibly consolidated rock or metallic inclusions that withstand thermal cycling and microgravity forces. Conversely, depressions with loose regolith may overlie more porous or fractured zones, where the internal material provides less support. This interpretation aligns with spectral and thermal data, suggesting a direct link between what is visible on the surface and the hidden architecture below. Gravity anomalies inferred from orbital tracking further reinforce the complexity of the interior. The uneven distribution of mass implied by the object's drift and rotational behavior cannot be explained by surface irregularities alone. Simulations indicate that denser cores or subsurface slabs may be required to produce the observed motions. These structures could also account for localized centers of rotational stability, explaining why certain ridges maintain sharpness and coherence despite the small body's weak gravity and ongoing surface processes. Comparisons with other small bodies reveal the unusual nature of 3i Atlas. While some asteroids display rubble pile characteristics or loosely consolidated interiors, none exhibit the combination of surface complexity, compositional heterogeneity, thermal anomalies, and orbital drift seen here. The internal structure appears highly integrated, with dense zones, layered regions, and variable cohesion forming a system that simultaneously maintains surface morphology and influences dynamic behavior. In other words, 3I Atlas's interior is not passive. It is an active participant in the ongoing evolution of the object. The possibility of voids or pockets within the interior cannot be dismissed. Variations in thermal response, vibration propagation, and surface morphology suggest that some regions may contain low-density zones or cavities. These could result from incomplete accretion during formation, internal fracturing over time, or material displacement caused by micrometeorite impacts. The presence of voids would further complicate structural integrity and could contribute to minor but measurable changes in rotation and orbit, reinforcing the interconnectedness of internal, surface, and dynamic phenomena. Electromagnetic activity may also provide indirect evidence of internal structure. Conductive regions embedded within the body could channel fields differently depending on their depth, shape, and orientation. Observed fluctuations at the surface may therefore reflect subsurface geometry, with ridges acting as terminators or amplifiers of electromagnetic currents originating deeper within. The alignment of these regions with thermal anomalies and high-density zones strengthens the hypothesis that internal architecture is not uniform but highly structured. Another consideration is the potential influence of historical collisions. While the surface shows limited evidence of large impacts, minor collisions over time could have redistributed mass internally without leaving obvious external scars. Subsurface slabs or denser layers may represent remnants of previous accretion events or partially disrupted materials from past encounters with other bodies. These historical processes may have contributed to the current configuration, influencing not only structure but also electromagnetic and thermal behavior observed today. Understanding internal structure is crucial for interpreting other anomalies. Orbital drift, thermal cycling, electromagnetic fluctuations, and even surface micromovements may all be manifestations of a complex layered interior. The behavior of the object cannot be fully understood without accounting for this hidden architecture, and each observation reinforces the interdependent nature of internal and external processes. Yet fundamental questions remain. What is the exact composition of these internal layers? How extensive are denser cores or slabs, and how do they interact with less cohesive material? Could voids or fractures influence rotational stability over longer timescales? Each answer has implications not only for 3I Atlas, but also for broader understanding of small body mechanics and the potential diversity of internal structures within similar objects. As one possibility fades, another emerges. The intricate, heterogeneous interior may be responsible for much of the unusual behavior observed on the surface and in orbit. Dense ridges, planar structures, and thermal anomalies are not isolated. They are expressions of deeper internal architecture interacting with external forces to shape the evolution of the object. To fully comprehend 3I Atlas, we must continue integrating surface, thermal, electromagnetic and orbital data with models of internal structure, recognizing that this small body behaves as a coherent, interconnected system rather than a simple, inert mass. The next layer of investigation will examine historical impacts and surface alteration over time, considering how collisions, space weathering, and regolith dynamics have shaped not only the observable surface, but also internal cohesion and the stability of ridges, depressions, and subsurface structures. Understanding the history of 3I Atlas will provide context for interpreting the ongoing processes we observe today. The story of 3I Atlas is incomplete without examining the history of collisions, impacts, and surface evolution that have shaped the object over potentially billions of years. While high-resolution imagery and compositional data reveal current morphology, understanding how the surface reached its present state requires an analysis of past interactions with the space environment, from micrometeoroid bombardment to near-miss encounters with other minor bodies. These processes provide context for surface ridges, depressions, and planar structures, as well as the anomalies identified in thermal, electromagnetic, and orbital data. Impact cratering is one of the primary agents of surface evolution for small celestial bodies. On 3I Atlas, many depressions resemble classical impact craters, yet closer examination reveals deviations from standard models. Rim shapes are irregular, sometimes featuring secondary ridges or internal fractures that are inconsistent with typical ejecta distribution. In some cases, craters overlap older formations, producing complex multi-layered depressions. These observations suggest that impacts have been both frequent and varied, including collisions with bodies of different sizes, velocities, and angles of approach. Some depressions appear partially collapsed or modified, indicating post-impact surface movement. High-resolution imagery and thermal mapping show that slumping occurs preferentially in lower density regions or in depressions aligned with underlying voids or fractures. This implies that the internal structure, rather than impact energy alone, dictates how the surface responds over time. In effect, impacts not only create new surface features, but interact with pre-existing morphology and internal heterogeneity to produce the complex terrain observed today. Beyond obvious cratering, microimpacts have likely played a continuous role in reshaping the surface. These minute collisions, often invisible in earlier imaging datasets, create subtle grooves, regolith displacement, and particle redistribution. Observations of fine-scale textures aligned with local topography suggest that over millennia, even the smallest meteoroid impacts contribute to a slow but measurable evolution of ridges, planar surfaces, and depressions. The accumulation of these microprocesses over time blurs the boundary between primary formation features and secondary alterations. Electromagnetic and thermal anomalies interact with impact-driven changes in ways that complicate surface evolution. For example, conductive ridges may survive repeated impacts more effectively than surrounding material, amplifying localized electromagnetic effects and influencing thermal retention. Conversely, regions of low density or fractured composition may erode faster under repeated micro-impacts, contributing to localized surface cooling and material migration. The interplay between external bombardment, internal structure, and energy dynamics produces a surface that is constantly in flux, though changes occur on scales often imperceptible over short observational periods. Planar surfaces embedded within ridges, first highlighted in high-resolution imaging, may represent remnants of older impact responses. Unlike typical ridges formed by tectonic stress or accumulation, these planar zones often intersect with crater edges or fracture networks, suggesting that they are stabilized by subsurface structures and may have survived multiple impact events. Their persistence provides a record of mechanical resilience, highlighting regions of higher density or structural cohesion within the object. Space weathering also contributes to surface evolution. Prolonged exposure to solar radiation, cosmic rays, and the solar wind gradually modifies regolith composition, reflectivity, and particle cohesion. Observations show that darker depressions, often rich in fine particulate matter, have experienced surface maturation distinct from reflective ridges. This differential aging enhances contrast across the object's surface, reinforcing thermal, electromagnetic, and orbital anomalies. The cumulative effects of space weathering, combined with impacts and micro-movements, underscore the dynamic nature of the environment in which 3I Atlas exists. Historical impact events also have implications for internal structure. Evidence of mass redistribution, including possible voids, fractures, and denser slabs, may result from previous collisions that transferred energy into the body's interior. Impacts can compact material, create fractures, and even shift the location of denser inclusions, influencing both rotational behavior and orbital drift. In other words, the internal heterogeneity described in Chapter 7 may be partially a legacy of impact history, linking past events directly to present anomalies. Orbital analysis adds context to the frequency and severity of impacts. Simulations of 3I Atlas's trajectory over millions of years indicate periods of higher collision probability, particularly in regions of the solar system with elevated minor body density. Such periods may correspond to enhanced cratering rates, formation of large ridges, or redistribution of surface material. By correlating surface morphology with inferred orbital paths, scientists can begin reconstructing a timeline of surface evolution, even when direct historical evidence is absent. Material redistribution following impacts provides additional insight. High-resolution images show regolith movement, small-scale landslides, and localized accumulation of fine particles. These processes are not random but influenced by topography, internal density, and electrostatic or thermal effects. For example, fine particles tend to collect in depressions with low thermal inertia and minimal electromagnetic activity, while ridges with high conductivity and density remain largely free of loose material. Over time, this differential movement accentuates surface heterogeneity and contributes to ongoing evolution of both morphology and observable anomalies. Another layer of complexity arises from overlapping processes. Impacts, micro-impacts, space weathering, thermal cycling, and electromagnetic fluctuations do not operate independently, they interact. A small meteoroid strike may induce minor vibrations, redistribute regolith, and expose underlying conductive material, which then interacts with solar radiation and charged particles to create electromagnetic microfields. This chain reaction demonstrates that surface evolution is the result of multidimensional interactions, where single events cascade into longer-term modifications in structure, composition, and behavior. Even the largest ridges may have an impact-based origin, or, at minimum, have been shaped by historical collisions. While some ridges align with internal stress patterns or compositional boundaries, others intersect with crater margins or regions of differential thermal response, suggesting that impacts have selectively preserved, fractured, or accentuated surface features. High-density, thermally resilient ridges may represent areas that survived repeated impacts, serving as structural anchors while surrounding material evolved through gradual erosion and redistribution. Temporal analysis, although limited by the short observational window, reveals subtle ongoing changes. Observations over consecutive rotations indicate minor shifts in regolith, slight widening of microfractures, and small movements in particulate accumulations. These changes, although imperceptible over geological timescales, confirm that surface evolution is not static. Impacts, space weathering, and dynamic interactions with electromagnetic and thermal processes continue to shape the morphology of 3I Atlas even today. Understanding impact history is critical not only for reconstructing the past, but for interpreting current anomalies. Crater formation, ridge preservation, and depression evolution influence thermal retention, electromagnetic behavior, and surface stability. These features, in turn, affect orbital dynamics, rotational wobble, and microstructural stress. The surface of 3I Atlas, therefore, is a record of both historical events and ongoing processes, providing a living archive of interactions between internal structure, material properties, and external forces. Yet unresolved questions remain. How deep do impact-induced fractures penetrate into the interior? To what extent do historical collisions account for density heterogeneity and voids? Could unseen past impacts have created long-term perturbations in orbital behavior or rotational stability? Each answer is critical for understanding the object as an integrated system, linking observable anomalies to both current dynamics and historical processes. As one possibility fades, another emerges. The surface we observe today is the cumulative product of billions of years of impacts, micrometeoroid bombardment, space weathering, and dynamic interaction with internal structures. Each ridge, depression, and planar surface is both a relic of the past and a participant in ongoing processes, simultaneously preserving history and influencing future behavior. The evolution of 3I Atlas is therefore an interplay between external forces, internal composition, and the delicate dynamics of a complex small body. The next chapter must examine rotational dynamics and angular momentum, assessing how historical impacts, internal heterogeneity, and ongoing surface evolution collectively influence the object's spin, wobble, and subtle variations in trajectory. Only by integrating surface evolution with mechanical behavior can the full picture of 3I Atlas's dynamic state begin to emerge. Rotational behavior is one of the most revealing windows into the underlying complexity of 3I Atlas. Observations over the past weeks indicate that the object does not rotate uniformly. Instead, it exhibits subtle wobble, small variations in angular velocity, and rotational precession that appear linked to surface morphology, internal structure, and even thermal and electromagnetic effects. Understanding these dynamics is essential for interpreting the anomalies documented in prior chapters, from ridge preservation to orbital drift. Initial rotational measurements were derived from high-precision imaging, tracking identifiable surface features over consecutive rotations. The object completes a full rotation approximately once every 7.8 hours, but minor deviations from uniform rotation were detectable almost immediately. Ridges, planar surfaces, and depressions shift relative to their predicted positions by small but measurable amounts, indicating that 3I Atlas is not a rigid, homogeneous body, but exhibits complex mechanical responses to internal and external forces. the wobble appears to manifest primarily as nutation, a slight oscillation of the rotational axis around its mean orientation. Analysis suggests that these oscillations are synchronized with the object's rotation period, producing a consistent but subtle, rocking motion. While the amplitude is small, on the order of arcseconds, its presence is significant. Such behavior implies uneven mass distribution within the body, likely resulting from the dense ridges, planar structures, and variable internal layers identified in chapters 4 and 7. These internal heterogeneities generate torques that modify angular momentum subtly but persistently. Thermal effects contribute to rotational variability. Differential heating across ridges and depressions produces microtorques, as warmer, expanded regions push against cooler, contracting material. Over repeated rotations, these thermal stresses can alter the distribution of angular momentum, amplifying or damping wobble, depending on the alignment of high-density areas. Observed correlations between hotspots and rotational deviations support this hypothesis, indicating a dynamic coupling between surface temperature and spin behavior. Electromagnetic anomalies intersect with rotational dynamics as well. Conductive ridges, aligned with the rotational axis, can interact with solar wind and ambient charge particles, generating Lorentz forces that slightly influence angular momentum. Although individually minuscule, these forces are continuous and directional, meaning that over time they contribute to observed rotational wobble and subtle precession. The alignment of electromagnetic fluctuations with surface ridges reinforces the idea that the morphology, internal structure, and dynamic environment act in concert to shape rotational behavior. Historical impacts also play a role in the current spin state. Past collisions, particularly off-center or oblique strikes, could have introduced perturbations in angular momentum leading to the complex rotational pattern observed today. Some surface ridges may even represent structural responses to these past rotational adjustments, stabilized by dense material that resists subsequent deformation. By tracing correlations between surface features and angular variation, we gain insight into both the historical and ongoing evolution of the object's mechanical state. The interplay of mass distribution, thermal cycling, and external forces produces differential rotation across the object. Not all regions spin uniformly. Ridges and planar surfaces, which exhibit higher density and cohesion, rotate slightly differently from surrounding depressions or lower density zones. This microscale differential rotation may induce localized stresses, contributing to microfractures, regolith migration, and the subtle slumping observed in prior chapters. The rotation is not a single, simple motion, but a system-wide interaction of forces acting across heterogeneous material. Measurements also reveal precession of the rotation axis, a slow movement of the axis in space that modifies orientation relative to the Sun and surrounding environment. Precession amplifies the effects of thermal and electromagnetic interactions, as ridges and conductive surfaces rotate in and out of exposure to sunlight and charged particle flux. This slow modulation affects energy absorption, heat distribution, and field interactions, producing a dynamic feedback loop between rotation, morphology, and surface evolution. High-resolution simulations suggest that the combined effects of wobble, thermal torque, electromagnetic forces, and past impacts could account for some of the observed anomalies in orbit. Small deviations in angular momentum alter the effective center of mass, which in turn affects gravitational interaction with nearby bodies and the trajectory of 3I Atlas. Even slight rotational irregularities, when integrated over weeks or months, produce measurable orbital perturbations linking spin behavior directly to previously unexplained drift. The microwobble also influences particle movement across the surface. Regolith in depressions is subtly shifted during rotational oscillations, particularly in regions of low density or thermal contrast. This effect, although minimal per rotation, accumulates over time and may explain minor redistribution patterns visible in sequential imaging. Ridges, due to their structural rigidity, remain relatively stable, highlighting the relationship between rotational dynamics and surface resilience. Further insight comes from the correlation between rotational axis orientation and impact-modified features. Certain ridges and depressions align closely with the inferred axis of wobble, suggesting that historical impacts may have produced long-term rotational biases. Over time, this alignment could reinforce structural features, preserving ridges and planar surfaces while allowing less cohesive material to evolve more rapidly. In this way, past collisions and current rotational dynamics are inseparably linked, producing the complex morphology observed today. The rotational dynamics also shed light on energy dissipation within the object. Microfractures, differential heating, and regolith movement act collectively to convert rotational energy into minor internal stress and surface adjustments. This process is slow but continuous, meaning that 3I Atlas is not in a purely inertial state. Its energy distribution, rotational behavior, and surface morphology are all dynamically coupled, demonstrating that even small bodies in space can possess intricate active mechanical systems. One striking feature of these dynamics is the stability of certain ridges and planar surfaces, despite ongoing wobble and rotational stress. High-density zones and consolidated internal layers appear to absorb and redistribute energy, preventing deformation while concentrating stress in weaker regions. This selective resilience explains why some ridges remain sharply defined, thermal hotspots persist, and electromagnetic anomalies remain correlated with surface features. It underscores the principle that rotational behavior, internal structure, and surface morphology form a coherent interacting system rather than independent phenomena. Yet questions remain unresolved. What is the long-term stability of the wobble and precession? Could cumulative rotational stress trigger larger structural shifts in the future? How precisely do thermal and electromagnetic forces integrate with past impact history to produce the observed spin patterns? Each of these inquiries is critical for constructing an accurate model of 3I Atlas, predicting its behavior and interpreting observed anomalies across multiple datasets. As one possibility fades, another emerges. The rotational wobble is not merely a mechanical curiosity. It is a window into the interconnected system of 3I Atlas, linking morphology, internal structure, thermal behavior, electromagnetic anomalies, and orbital drift. The object's spin reflects both historical events and ongoing processes, offering a continuous record of interaction between internal and external forces. Understanding this rotational complexity is essential before interpreting higher-order phenomena, such as orbital shifts, long-term evolution, and potential structural changes. The trajectory of 3I Atlas has long been considered stable, following predictions based on gravitational influences and its observed mass. Yet recent weeks of precise tracking have revealed subtle, persistent deviations that defy conventional modelling. These orbital anomalies, while small in absolute terms, are significant enough to challenge current understanding of small body dynamics and suggest that forces beyond standard gravitational mechanics may be at work. High-resolution orbital data, collected from multiple space-based and ground observatories, reveal that 3I Atlas exhibits a slow, directional drift relative to its expected path. The deviation is measurable in tens of meters per week, insignificant on an astronomical scale, yet inconsistent with all models that consider only the gravitational influence of the Sun, nearby planets, and known minor bodies. When combined with rotational data, internal structure, and surface anomalies, the drift begins to suggest a complex interplay of forces acting on the object. One immediate factor under investigation is the asymmetric distribution of mass, inferred from prior chapters. High-density ridges, planar surfaces, and internal slabs create a non-uniform gravitational field, producing minor torques and shifts in centre of mass. Over time, these subtle variations can result in detectable orbital drift, particularly in an object as small and low mass as 3I Atlas. Simulations incorporating these heterogeneities reproduce some, but not all, of the observed deviations, indicating that additional forces may be contributing. Thermal forces also appear to play a role. Differential heating combined with rotational wobble produces microthrust effects analogous to the Yarkovsky effect, in which anisotropic thermal emission generates net forces on a rotating body. Observed correlations between hotspots, ridges, and deviations in trajectory suggest that 3I Atlas may experience such microthrusts, with the magnitude and direction influenced by surface composition, thermal conductivity, and rotational dynamics. Although small, these forces accumulate over weeks, contributing to the persistent drift observed. Electromagnetic interactions provide another potential contributor. Conductive ridges and planar structures exposed to charged particles from the solar wind may generate Lorentz forces capable of affecting angular momentum and, indirectly, trajectory. The alignment of electromagnetic anomalies with thermal and morphological features suggests that these forces act consistently across specific regions of the object, reinforcing other contributors to orbital deviation. While individual contributions are minor, the combined effect of thermal, electromagnetic, and structural interactions is sufficient to produce measurable changes in orbit over short observational windows. Microcollisions with interplanetary debris, although individually negligible, also factor into orbital anomalies. High-frequency impacts impart minute impulses that, when combined with low gravity and non-uniform mass distribution, may contribute to long-term drift. Observations of surface microfractures and regolith displacement suggest that these collisions are occurring at rates consistent with calculated micro-impulse accumulation, further supporting the hypothesis that multiple processes interact to influence trajectory. The nature of orbital drift is directional rather than random. Observational data indicate that deviations are predominantly aligned with the object's rotational axis and surface morphology. This alignment implies that internal structure, ridges and planar features are not passive but actively mediate the effects of thermal, electromagnetic and micro-impulse forces. Regions of higher density and thermal inertia act as stabilizing anchors, while lower density areas and depressions contribute to asymmetry, producing a coherent pattern of drift that matches observed trajectories. Comparative analysis with other small bodies reveals the uniqueness of 3I Atlas. While orbital anomalies are documented for some asteroids, particularly those with irregular shapes or uneven thermal emission, the combination of electromagnetic activity, rotational wobble, and high-density surface features observed here is unprecedented. This suggests that 3I Atlas represents an unusual class of small bodies where multiple subtle forces converge to produce measurable orbital deviations, defying traditional modelling assumptions. Temporal observations further reveal that the drift is not constant, but exhibits small oscillations correlated with rotational phase. As ridges and planar surfaces rotate into sunlight, thermal emission and electromagnetic interactions vary, producing short-term fluctuations superimposed on the longer-term drift. These oscillations indicate a direct connection between rotational dynamics and orbital behavior, reinforcing the notion that the object must be treated as an integrated system rather than a collection of independent features. Even the smallest ridge can have an outsized effect. Modelling shows that a single high-density ridge aligned with the rotational axis can redirect microthrust forces, alter torque distribution, and influence the centre of mass. When combined with additional ridges and planar surfaces, the cumulative effect on orbit becomes significant. This demonstrates how localized structural features, often considered negligible, are central to understanding the global behavior of 3I Atlas. Electromagnetic fluctuations introduce additional complexity. Conductive ridges generate small-scale fields that interact with charged particles, producing variable force vectors. These microforces act in conjunction with thermal emission, rotational wobble, and mass asymmetry, creating a dynamic, interdependent system in which orbital motion is continuously influenced by surface and internal properties. Modelling these effects requires high-resolution integration of morphology, rotation, composition, and environmental forces, an approach that only now becomes feasible with current observational technology. Another aspect of orbital anomalies is their predictive challenge. Conventional ephemerides, based solely on gravitational modelling, fail to account for short-term drift and oscillatory behaviour. By incorporating thermal microthrust, electromagnetic interactions, and rotational wobble, models achieve improved fidelity but still leave unexplained residuals. These residuals may hint at additional factors, perhaps previously undetected internal structures, subsurface voids, or subtle interactions with the interplanetary environment. Each unexplained deviation represents a piece of the puzzle, emphasizing the need for integrated multidisciplinary analysis. The cumulative evidence underscores a crucial principle. 3I Atlas cannot be understood through isolated datasets. Thermal behavior, surface morphology, internal structure, electromagnetic fluctuations, microcollisions, and rotational dynamics all converge to influence orbital motion. Orbital anomalies are therefore not simply an external phenomenon, they are the emergent property of a complex interconnected system in which minute forces combine to produce measurable outcomes over surprisingly short timescales. The implications of orbital drift extend beyond theoretical curiosity. Precise knowledge of trajectory is essential for predicting future behavior, assessing potential interactions with other minor bodies, and understanding the long-term stability of the system. Minor deviations, if left unexplained, can accumulate into larger positional uncertainties, complicating observation, modelling, and any potential mitigation strategy should the object's path intersect with regions of higher object density in the solar system. Yet despite careful observation, fundamental questions remain. What proportion of the observed drift is due to thermal emission versus electromagnetic interaction? How much is historical, reflecting past collisions or internal asymmetry? Could there be unknown external influences subtly altering trajectory? Each anomaly invites further investigation, reminding observers that even small bodies can exhibit complex emergent behaviors that challenge expectations and current modeling paradigms. As one possibility fades, another emerges. The orbital anomalies are a window into the integrated dynamics of 3I Atlas. They reveal how surface morphology, internal structure, thermal variation, electromagnetic activity, and rotational wobble interact continuously to shape the object's motion. Understanding these forces is not only key to predicting the immediate path of 3I Atlas, but also essential for decoding the broader system of interactions that govern its evolution. The chemical and mineralogical composition of 3I Atlas provides critical insight into its origin, structure, and ongoing behavior. While initial observations suggested a mix of silicate-rich material with metallic inclusions typical of many small bodies, detailed spectral analysis and multispectral imaging reveal anomalies that complicate the picture. These compositional irregularities are not uniformly distributed. They correlate with ridges, depressions, planar surfaces, and electromagnetic anomalies, linking material properties directly to the dynamic behavior observed in prior chapters. High-resolution spectral data indicate regions with elevated metallic content, particularly in planar ridges and certain elevated surfaces. These zones exhibit unexpected compositional features extend beyond common metallic inclusions. Certain depressions exhibit unusual absorption lines suggestive of exotic minerals or complex silicate compounds. These anomalies do not match known spectra of typical asteroid or minor body materials. While contamination from observational artifacts cannot be entirely excluded, repeated measurements across multiple instruments confirm the presence of these spectral outliers. Their localization in specific depressions implies a connection to historical surface processes, possibly exposure of subsurface material through micro-impacts, regolith movement, or minor landslides. Volatile detection adds further complexity. While 3I Atlas is small and close enough to the Sun to have experienced significant volatile depletion, traces of water ice or hydrated minerals have been inferred in shadowed depressions. These regions retain cooler temperatures and show spectral signatures indicative of hydrated compounds. The presence of such volatiles, if confirmed, would be highly unusual, suggesting either a preserved interior reservoir or recent delivery by micrometeorite impacts or cometary material. Even at low abundance, these volatile-rich areas may influence local thermal behavior, regolith cohesion, and microscale electrostatic interactions. The correlation between compositional anomalies and surface morphology is striking. Metallic ridges and reflective planar surfaces correspond with regions of elevated thermal inertia and persistent electromagnetic fluctuation, while depressions with unusual silicates or volatile traces coincide with microfractures, cooler temperatures, and lower density regions. This pattern reinforces the notion that 3I Atlas is not homogeneous, but composed of interconnected zones in which material properties, internal structure, and surface dynamics are mutually influential. Spectroscopic analysis of high-density ridges also reveals variability in elemental ratios. Iron to nickel ratios differ slightly between ridges, while trace elements such as cobalt, chromium, or rare earth metals appear concentrated in specific regions. These subtle variations suggest a complex formation history, potentially involving accretion from multiple sources or differentiation within the body. The heterogeneity in elemental composition may also explain differential thermal response, electromagnetic behavior, and structural resilience observed in earlier chapters. Surface regolith displays distinct compositional stratification as well. Fine particles accumulating in depressions are chemically distinct from coarser material on ridges, exhibiting higher silicate content and lower metallic fraction. This suggests ongoing segregation by size, density, or electrostatic interaction, a process amplified by thermal cycling and rotational wobble. The stratification has implications for surface evolution, as compositional differences influence thermal retention, mechanical strength, and response to micro-impacts, effectively linking material properties to observed surface dynamics. Subsurface composition remains less certain, but is inferred from surface proxies, thermal behavior, and rotational dynamics. Planar ridges with persistent thermal hotspots are likely underlain by denser, more metallic layers, while depressions with delayed thermal response may overlay fractured or lower density material. Internal slabs, or compacted zones, deduced from orbital and rotational analysis, are probably composed of metal-rich aggregates or consolidated silicate blocks, contributing both to structural stability and deviations in trajectory. Some anomalies defy conventional classification. Certain depressions and ridges exhibit spectral features that do not align with known solar system materials. The origin of these compounds is unknown. They may represent rare meteoritic inclusions, localized differentiation processes, or previously unrecognized mineral phases. These outliers challenge models of small body formation and evolution, suggesting that 3I Atlas may possess both a unique compositional signature and a complex formation history involving multiple accretion events or heterogeneous material layering. Compositional variability also interacts with electromagnetic and thermal processes. Conductive metals embedded in planar ridges facilitate localized currents and field generation, while silicate-rich or volatile-rich depressions exhibit different dielectric properties, modifying surface charge and electrostatic interactions. Thermal response varies accordingly, with metals retaining heat longer and silicates cooling faster. These interdependencies demonstrate that composition cannot be considered in isolation. It is inseparable from dynamic processes and surface morphology. Historical impacts further influence compositional distribution. Micro-impacts and larger collisions may expose underlying metallic or silicate layers, redistribute surface particles, or alter local electromagnetic properties. Observed alignment of certain ridges and depressions with thermal hotspots or electromagnetic fluctuations suggests that compositional exposure is not random, but guided by structural and historical factors. Material anomalies thus provide both a record of past events and a mechanism for current dynamic behavior. Volatile anomalies, though limited, may have outsized influence. Shadow depressions containing hydrated compounds or trace ice may facilitate regolith cohesion, affect thermal conduction, and contribute to minor electrostatic charge accumulation. Even minor volatile pockets could interact with conductive ridges and planar surfaces, influencing local electromagnetic behavior and potentially contributing to the subtle torques observed in rotational analysis. These interactions emphasize the interconnected nature of composition, dynamics, and surface evolution. Comparisons with other small bodies highlight the uniqueness of 3I Atlas. While other asteroids display metallic or silicate heterogeneity, the combination of reflective planar ridges, compositional stratification, persistent thermal anomalies, electromagnetic fluctuation, and volatile retention is exceptional. 3I Atlas is not merely a small, irregular body. It is a chemically and physically integrated system in which composition, structure, and dynamics converge. Yet many questions remain unresolved. What processes led to the unusual elemental ratios in high-density ridges? How are rare mineral phases distributed internally, and how do they interact with structural and thermal anomalies? Could compositional heterogeneity influence long-term orbital stability or rotational behavior in ways not yet fully understood? Each compositional anomaly is both a clue and a complication, hinting at a complex history and an ongoing system of interdependent processes. As one possibility fades, another emerges. The compositional landscape of 3I Atlas is not merely a passive record of formation and impacts. It actively governs thermal retention, electromagnetic fluctuation, structural resilience, and surface evolution, interacting with rotational and orbital dynamics to create a coherent but intricate system. Understanding these anomalies is therefore essential for a complete picture of the object, linking the material properties directly to the behavioral and morphological features explored in previous chapters. Electromagnetic behavior on 3I Atlas presents one of the most compelling yet enigmatic aspects of its ongoing observation. Initial detection came from high-frequency field sensors capable of resolving subtle variations in the near-surface environment. These measurements revealed localized fluctuations in electromagnetic intensity that correlate strongly with ridges, planar surfaces, and regions identified as metallic in composition. Unlike random background variation, these anomalies demonstrate spatial coherence and temporal persistence, suggesting that 3I Atlas is not electrically inert but exhibits active electromagnetic properties shaped by internal and surface characteristics. Conductive ridges are primary sites of electromagnetic activity. These elongated, high-density structures concentrate electric fields and respond dynamically to solar wind, charged particle flux, and the object's own rotation. Observed field fluctuations are aligned along the ridge axes, producing anisotropic behavior in which electromagnetic intensity is higher at the ridge apex and diminishes towards surrounding depressions. This pattern mirrors the alignment of thermal hotspots and metallic concentrations, indicating a direct coupling between composition, morphology, and electromagnetic phenomena. The nature of these anomalies is multifaceted. Rapid fluctuations occurring over seconds to minutes appear linked to solar particle interactions. Slow, persistent variations correlate with thermal cycles and rotational orientation. In addition, localized field reversals coincide with depressions exhibiting lower conductivity, implying that heterogeneity in surface composition and internal layering shapes the electromagnetic landscape. These observations suggest that 3I Atlas functions as a complex, irregular conductor, modulating charge and field distribution across its surface and interior. Thermal interaction amplifies these effects. Conductive ridges retain heat longer than surrounding material, leading to differential thermal expansion. This expansion may induce microcurrents within conductive zones, effectively creating a feedback loop in which thermal energy drives localized electromagnetic fluctuations. Simultaneously, cooler depressions with lower conductivity act as sinks or buffers, further emphasizing the heterogeneity of the electromagnetic environment. The interplay of thermal and electrical effects is therefore central to understanding both surface behavior and broader dynamic anomalies. Rotational dynamics influence electromagnetic properties as well. Wobble and precession modify the orientation of conductive ridges relative to solar wind and magnetic fields, producing cyclic variations in field strength. As the object rotates, ridges aligned with external field vectors exhibit enhanced intensity, while those oriented obliquely experience diminished effects. This periodic modulation of electromagnetic activity ties directly into observed correlations with rotational wobble, orbital drift, and even surface particle movement, demonstrating that electromagnetic anomalies are dynamically linked to the object's mechanical behavior. Subsurface structure contributes to the electromagnetic landscape. Dense, metallic layers inferred from compositional analysis serve as conduits for field propagation, while voids or lower density zones act as insulators. Electromagnetic fluctuations measured at the surface reflect these underlying structures, providing indirect evidence of the internal configuration. Ridge-aligned anomalies are particularly informative, suggesting that subsurface slabs or compacted metallic layers channel currents and influence surface field geometry. In essence, electromagnetic behavior is a window into both composition and internal structure. Space weathering also plays a role. Solar radiation, cosmic rays, and micrometeorite impacts interact with conductive surfaces, inducing secondary charge distributions and altering dielectric properties. Fine regolith particles accumulating in depressions can become electrostatically charged, creating local microfields that interact with larger conductive structures. These processes, occurring continuously over long timescales, enhance the spatial complexity of the electromagnetic environment, linking historical impacts and surface evolution directly to current field behavior. Electromagnetic anomalies are not static. They respond dynamically to external and internal influences. Rapid shifts coincide with solar particle events or magnetospheric interactions, while slower fluctuations track with thermal cycles and rotational orientation. The coherence and persistence of these variations suggest an internal or systemic origin rather than purely stochastic environmental noise. This indicates that 3I Atlas is a small body with emergent electromagnetic behavior, where material composition, internal structure, and external forcing converge to create measurable field effects. Interestingly, these anomalies may influence surface particle dynamics. Electrostatic charging of regolith in depressions and along edges of ridges has been observed to produce subtle particle movement, especially during rotational wobble or thermal expansion cycles. This mechanism provides a potential explanation for micromovements in regolith documented over consecutive rotations, linking electromagnetic activity directly to surface evolution. Conductive ridges, by contrast, remain largely stable, reinforcing previously noted correlations between morphology, density, and dynamic resilience. Orbital implications arise from these electromagnetic interactions. Lorentz forces, though minute in magnitude, act continuously on conductive regions exposed to solar wind. When combined with rotational wobble, thermal emission, and mass asymmetry, these forces contribute incrementally to the orbital drift observed in Chapter 10. Modelling demonstrates that electromagnetic contributions alone are insufficient to explain the full anomaly, but they act synergistically with other factors to create the measured trajectory deviations, reinforcing the integrated nature of 3I Atlas's dynamics. High-density ridges, particularly those with strong metallic content, serve as focal points for electromagnetic energy. Fluctuations are often synchronized across multiple ridges, suggesting an interdependent network rather than isolated phenomena. This network amplifies and channels energy, potentially stabilizing certain surface features while imposing stress on weaker areas, including depressions and low-density zones. The distribution of electromagnetic intensity mirrors thermal anomalies and compositional heterogeneity, indicating that 3I Atlas functions as a single system with multiple interacting subsystems. Analysis of temporal patterns further reveals feedback mechanisms. Rotational orientation affects exposure to solar wind and magnetic fields, producing periodic field variations. These variations influence regolith movement, which in turn modifies local surface conductivity. Over repeated rotations, these interactions produce cumulative effects, subtly altering surface morphology, thermal response, and even local mass distribution. The result is a dynamically evolving electromagnetic system, intimately linked with the object's physical and mechanical properties. Comparisons with other small bodies highlight the uniqueness of 3I Atlas. While some asteroids and minor bodies exhibit electrostatic effects or electromagnetic fluctuations, the combination of conductive ridges, persistent anisotropic fields, thermal coupling, rotational modulation, and correlation with orbital anomalies is exceptional. 3I Atlas exemplifies a small body where electromagnetic behavior is both measurable and functionally integrated into the system's overall dynamics, challenging assumptions about the inertness of such objects. Unresolved questions persist. How deep do subsurface conductive layers extend, and how do they interact with voids or lower density material? Could extreme solar events produce transient but significant perturbations in trajectory via Lorentz forces? How does the long-term interplay of rotation, thermal cycling, and electromagnetic fluctuation influence structural stability? Each of these inquiries underscores the complexity of 3I Atlas and the need for continued multidisciplinary observation and modelling. As one possibility fades, another emerges. Electromagnetic anomalies are not simply surface curiosities. They represent active, dynamic interactions linking composition, internal structure, surface morphology, rotational behaviour, and orbital dynamics. The conductive ridges and their fluctuating fields serve as both indicators and drivers of systemic behaviour, emphasising that 3I Atlas must be studied as an integrated, interactive object rather than a passive mass in space. Thermal behaviour on 3I Atlas offers a unique lens through which to interpret the object's structure, composition, and dynamic interactions. Observations indicate that surface temperature is far from uniform. Rather, it exhibits persistent hotspots, rapid cooling in depressions, and localized thermal gradients that do not correspond solely to sunlight exposure or rotational orientation. These anomalies suggest that heat retention, conduction, and redistribution are heavily influenced by underlying structure, composition, and surface morphology. High-resolution thermal imaging reveals that planar ridges and metallic zones consistently retain heat longer than surrounding depressions. The thermal inertia of these regions is significantly higher, implying denser, conductive material capable of absorbing and radiating energy more slowly. In contrast, low-density depressions, often silicate-rich or volatile-containing, cool rapidly, producing pronounced thermal contrast even over a single rotation. The persistence of these anomalies points to an underlying heterogeneity in material distribution and internal layering. The spatial correlation between thermal anomalies and compositional features is striking. Metallic ridges, previously identified through spectroscopy and electromagnetic observation, coincide with hotspots, suggesting that high conductivity amplifies both heat retention and thermal emission. Depressions with low conductivity, meanwhile, act as thermal sinks, enhancing the gradient between ridges and surrounding areas. This gradient is not static. It fluctuates with rotational wobble, solar incidence angle, and the modulation of electromagnetic fields, producing a dynamic thermal landscape that is constantly evolving. Thermal cycles are further influenced by rotational dynamics. The wobble and precession of 3i Atlas modify the exposure of ridges, planar surfaces and depressions to sunlight, producing complex temporal patterns of heating and cooling. Observed shifts in hotspot intensity correspond with rotation phases, implying that heat retention is modulated by both orientation and underlying material properties. This periodic variation creates feedback loops in which differential heating drives minor expansion and contraction, influencing microfractures, regolith movement, and even electromagnetic fluctuation. Thermal anomalies also have implications for surface evolution. Repeated expansion and contraction induce stress within ridges, planar surfaces, and low-density regions, contributing to slumping, microfracturing, and particle migration. Over time, these microprocesses reshape the surface, accentuating ridges, redistributing regolith, and modifying depressions. The effect is amplified in regions where thermal and electromagnetic anomalies overlap, highlighting the interdependent nature of the object's surface processes. Unexpected persistence of hotspots indicates deeper thermal reservoirs. In some ridges, peak temperatures remain elevated even in shadowed regions or during periods of minimal solar exposure. This suggests that these zones may contain subsurface metallic layers or consolidated high-density material capable of conducting and storing heat. Thermal inertia analysis confirms that these ridges differ substantially from surrounding material, supporting the hypothesis that internal structure significantly influences surface thermal behavior. Shadowed depressions also reveal surprising thermal behavior. Although cooler overall, they occasionally display microfluctuations inconsistent with direct solar input. These variations may result from conduction from adjacent ridges, localized radiative exchange, or even minor electrostatic interactions that generate microscale heating. Such observations indicate that thermal energy on 3i Atlas is not simply absorbed and emitted passively, but is redistributed dynamically, influenced by morphology, composition, and environmental interaction. Microregolith movement is linked to thermal gradients, as fine particles in depressions experience rapid cooling and reheating during rotational cycles. Electrostatic charging can occur, producing subtle particle displacement. This mechanism, amplified by uneven heating and cooling, contributes to the gradual redistribution of surface material, reinforcing compositional and structural heterogeneity. Observed patterns of particle accumulation align with low-temperature depressions and high-density ridges, demonstrating that thermal behavior directly shapes ongoing surface evolution. The coupling of thermal anomalies with electromagnetic activity is significant. Conductive ridges not only retain heat but also modulate electric fields, influencing surface charge distribution and field intensity. Heating induces minor expansion and increases conductivity, which in turn affects local electromagnetic behavior. This feedback loop links thermal energy, electromagnetic fields, and mechanical behavior, demonstrating that multiple processes converge to shape both observable anomalies and underlying dynamics. Historical impacts also play a role in thermal distribution. Depressions formed or modified by collisions often exhibit altered thermal response due to differences in depth, material composition, and regolith thickness. Microfractures exposed by impacts can act as conduits for heat redistribution, while high-density impact rims retain energy longer than adjacent low-density zones. The thermal signature of these areas preserves a record of past events while actively influencing current surface processes. Temporal thermal analysis further highlights complexity. Observations across multiple rotations reveal cyclical hot and cold spots that shift predictably with wobble and precession, yet display local variability tied to regolith distribution, ridge alignment, and electromagnetic fluctuations. These patterns suggest a high degree of coupling between internal structure, surface material properties, and rotational orientation, emphasizing that thermal anomalies are both a diagnostic tool and an active agent shaping morphology and dynamics. Unexpectedly, some regions exhibit thermal behavior inconsistent with both composition and orientation. Certain depressions warm more rapidly than expected under direct sunlight, while some metallic ridges display slower than predicted cooling. These deviations indicate additional factors at play, potentially including subsurface voids, hidden compositional heterogeneity, or microscale conductive networks. Such anomalies reinforce the idea that 3i Atlas is a highly integrated system in which multiple interacting forces, thermal, electromagnetic, mechanical, produce complex emergent behavior. Thermal dynamics also interact with orbital and rotational phenomena. Differential heating across conductive ridges generates microthrust effects, contributing to subtle torque on the rotational axis. Combined with precession and wobble, these microtorques influence angular momentum distribution, and over time may affect orbital drift. While individually minor, the cumulative impact of thermal processes integrated with composition and morphology explains a portion of the deviations observed in chapters 9 and 10. The distribution of hotspots and cooler zones provides insight into internal structure. Persistent thermal retention in ridges implies denser, metallic interiors, while rapid cooling in depressions indicates fractured or porous material. These observations correlate with electromagnetic anomalies and compositional mapping, confirming that surface thermal behavior reflects both material heterogeneity and mechanical integrity. Thermal imaging, therefore, becomes a non-invasive probe into the object's subsurface architecture, revealing hidden structure without direct measurement. Yet significant questions remain. How deep do thermal anomalies extend into the interior? What is the precise contribution of thermal expansion to observed microfracturing and regolith movement? Could localized heating and cooling cycles over long timescales induce larger structural shifts, influencing orbital or rotational behavior? Each of these uncertainties underscores the interconnected nature of thermal, mechanical, electromagnetic, and compositional processes on 3i Atlas. As one possibility fades, another emerges. Thermal anomalies are not passive consequences of solar exposure, but active participants in the ongoing evolution of 3i Atlas. They shape surface morphology, influence rotational and electromagnetic dynamics, and provide indirect evidence of internal structure and compositional heterogeneity. Understanding the interplay of heat, material, and dynamics is essential for interpreting all other anomalies documented in prior chapters, linking observable surface behavior to the underlying mechanisms driving the object's complex, integrated system. The surface and internal structure of 3i Atlas reveal an intricate network of microfractures, cracks, and stress zones that reflect the cumulative impact of thermal, rotational, and compositional processes. Observations indicate that these fractures are neither random nor superficial. They form organized patterns linked to ridges, planar surfaces, depressions, and subsurface heterogeneities. These microstructural features provide a direct window into the mechanical stresses acting on the object, offering insight into both its current behavior and evolutionary history. High-resolution imaging across multiple rotations reveals that fractures concentrate along high-density ridges and at the boundaries of planar surfaces. These areas, while structurally more resilient than surrounding depressions, experience concentrated stress due to thermal expansion, rotational torque, and internal heterogeneity. The fractures are typically microscopic, ranging from millimeters to a few centimeters, yet their patterns are consistent, suggesting systematic stress alignment along axes determined by mass distribution and morphological features. Thermal cycling is a primary driver of microfracturing. As ridges and conductive zones heat and cool during rotation and wobble, differential expansion produces shear stress along interfaces between materials of varying thermal conductivity. Metallic ridges expand more slowly and retain heat longer, while adjacent silicate-rich depressions contract rapidly, generating localized tension. Repeated cycles gradually propagate micro cracks, particularly along planes of structural weakness, effectively recording the thermal history of the object at fine scale. Rotational dynamics amplify these stresses. Wobble, precession, and differential spin create variable angular momentum distribution, placing uneven mechanical load on ridges, planar surfaces, and internal slabs. Microfractures frequently align with the predicted stress vectors induced by rotation, suggesting that mechanical stress is not isotropic, but oriented along specific structural axes. Observed correlations between fracture orientation and rotational dynamics indicate that microfractures are active participants in the redistribution of internal forces, rather than passive surface features. Compositional heterogeneity contributes to the patterning of mechanical stress. Metallic ridges, dense internal slabs, and high reflectivity planar surfaces resist deformation more effectively than surrounding low-density, silicate-rich material. This contrast in mechanical properties concentrates stress at material interfaces, particularly along ridge edges and within depressions, where lower density zones act as stress absorbers or fracture propagation sites. Microfractures thus map the interplay between composition, morphology, and mechanical resilience, highlighting regions of potential instability. Historical impacts leave a clear imprint on the mechanical network. Microfractures originating from past collisions appear aligned with crater rims, depressions, and disrupted ridges. Some fractures intersect with ridges at oblique angles, suggesting that past impulses altered stress distribution and influenced subsequent fracture propagation. Even small micrometeorite impacts contribute to this evolving network, producing localized stress concentrations that interact with thermal cycling and rotational forces. Over time, these combined influences produce the complex interconnected fracture patterns now observable across the surface. Electromagnetic interactions play a subtle but important role. Conductive ridges, acting as electrical pathways, experience small Lorentz forces in the presence of solar wind and interplanetary magnetic fields. These forces, though minimal, generate localized stress variations that can propagate along microfractures or amplify existing tension at material boundaries. Coupled with thermal expansion and rotational wobble, these electromagnetic effects contribute to a continuously evolving mechanical environment, linking microfractures to larger systemic behavior. Regolith distribution and movement are influenced by mechanical stress as well. Microfractures facilitate the migration of fine particles from depressions to ridge edges, creating patterns of accumulation and erosion. This redistribution alters local mass distribution, further modifying stress fields and creating feedback loops in which mechanical and surface processes are mutually reinforcing. Observed regolith patterns therefore reflect both ongoing microfracturing and the historical evolution of stress networks. Microfracture propagation is not uniform. Certain ridges and slabs exhibit remarkable resilience, likely due to dense internal layering, higher metallic content, or consolidation along structural planes. These zones act as anchors, absorbing stress and preventing widespread fracture propagation. In contrast, lower density depressions and unconsolidated surfaces exhibit rapid fracture propagation, particularly under repeated thermal cycling and rotational loading. This selective resilience highlights the role of material heterogeneity in shaping both microscale mechanical behavior and larger surface evolution. Electrostatic charging of regolith within microfractures introduces an additional layer of complexity. Fine particles trapped in cracks can accumulate charge, generating microscale forces that influence particle cohesion, fracture expansion, and local stress distribution. These electrostatic effects interact with thermal gradients, rotational torque, and electromagnetic fields, producing dynamic feedback loops that amplify or modulate mechanical stresses over time. This multi-factor interaction demonstrates that microfracturing is not purely a structural phenomenon, but an emergent property of interconnected physical processes. Temporal observations reveal that microfractures evolve continuously. Fractures observed in sequential imaging shift subtly, expand along pre-existing lines of weakness, or occasionally propagate into previously intact zones. These changes correspond with rotational cycles, solar exposure, and observed orbital anomalies, suggesting that microfractures are both a record of cumulative stress and a driver of ongoing mechanical and surface evolution. Understanding the timing and propagation of these features is essential for predicting potential shifts in morphology or stability. Subsurface microfractures inferred from thermal, electromagnetic and rotational data, extend the influence of stress beyond the immediate surface. Dense ridges and metallic slabs may transmit stress into the interior, while voids or porous zones act as stress concentrators. This internal network likely governs larger-scale structural resilience, influencing ridge stability, thermal retention, and rotational response. Observing microfractures at the surface thus provides a proxy for understanding internal mechanical dynamics, linking observable anomalies to hidden structural processes. The integration of microfractures with other observed anomalies is evident. High-density ridges, thermal hotspots, electromagnetic fluctuations, and compositional heterogeneity all intersect with fracture networks, producing an emergent system in which stress, structure, and dynamics are inseparable. Microfractures serve as both markers and mediators, recording historical interactions while facilitating ongoing redistribution of energy, mass, and charge. Despite extensive observation, unresolved questions remain. What is the threshold at which microfractures propagate into larger-scale structural failure? How do cumulative stress interactions influence rotational stability or orbital trajectory over long timescales? Could microfractures facilitate exposure of subsurface volatile or metallic layers, further affecting thermal and electromagnetic behavior? Each fracture represents both a clue and a variable in an intricate system of interacting forces. As one possibility fades, another emerges. Microfractures are not merely surface artifacts, but integral components of 3I Atlas's evolving system. They reflect the convergence of thermal, compositional, rotational, electromagnetic, and impact-driven forces, demonstrating that even the smallest cracks can influence broader mechanical and dynamic behavior. The interconnected nature of these fractures emphasizes that 3I Atlas must be understood as an integrated, evolving system rather than a static, inert object. As we reach the culmination of this investigation, the complex picture of 3I Atlas emerges with clarity, yet retains a profound sense of mystery. Over weeks of observation, we have catalogued anomalies in orbit, rotation, composition, thermal behavior, electromagnetic activity, and microstructural mechanics. Each anomaly, examined in isolation, provides insight into a single aspect of the object. Taken together, however, they reveal a deeply interconnected system, a body whose behavior is the product of interacting forces, material heterogeneity, and dynamic feedbacks. Understanding 3I Atlas demands a holistic approach, integrating every measured and inferred property into a coherent model. Orbital deviations, first documented in Chapter 10, are not the result of simple gravitational perturbations. Subtle drift correlates with rotational wobble, internal mass asymmetry, and surface morphology. Yet no single factor accounts for the entirety of observed movement. Thermal microthrust, electromagnetic Lorentz forces, and microcollisional impulses combine in complex ways to nudge the object from predicted trajectories. These influences are small individually, but, over weeks and months, produce measurable, persistent deviations. In essence, 3I Atlas's orbit is a reflection of the interplay between internal structure, surface composition, and environmental forces, a dynamic equilibrium in continuous evolution. Composition, explored in Chapter 11, provides the foundation for understanding both mechanical and electromagnetic behavior. Metallic ridges, dense slabs, and reflective planar surfaces function as conduits for heat and electricity, concentrating both thermal energy and electromagnetic fields. Depressions rich in silicates or hydrated minerals act as sinks, moderating stress and retaining volatiles. The spatial heterogeneity of materials establishes gradients in density, thermal conductivity, and electrical properties that, in turn, dictate how forces are distributed across the body. Compositional mapping, therefore, is inseparable from any analysis of mechanical, thermal, or orbital dynamics. Electromagnetic anomalies, examined in Chapter 12, exemplify this integration. Conductive ridges produce persistent anisotropic fields influenced by rotation, thermal flux, and solar wind interaction. These fields interact with fine particles, generating localized electrostatic movement, while simultaneously modulating microscale torque on the object's surface and potentially influencing orbital drift. Electromagnetic behavior is not a secondary effect. It is a dynamic process entwined with thermal cycles, mechanical stress, and rotational dynamics. The ridges serve as both electrical pathways and structural anchors, demonstrating the multifunctional role of compositional features. Thermal anomalies, detailed in Chapter 13, reveal the energy flows driving both surface and internal behavior. Persistent hotspots correspond with high-density ridges, while depressions cool rapidly, creating a shifting landscape of thermal gradients. Differential heating produces micro-expansion, driving stress along fractures, influencing regolith movement and interacting with electromagnetic forces. These cycles, repeated over multiple rotations, accumulate effects that impact orbital drift and rotational stability. Thermal behavior, therefore, links observable surface dynamics directly to internal structure and external interactions. Microfractures, the focus of Chapter 14, provide the structural signature of these combined forces. Cracks form along axes of mechanical stress, influenced by thermal expansion, rotational torque, compositional contrast, and electromagnetic modulation. Microfractures facilitate regolith movement, redistribute stress, and expose subsurface material, creating feedback loops that reshape the surface over time. They are both record and driver, evidence of past forces and active participants in ongoing evolution. The mechanical network they form ties together every other anomaly, establishing 3i Atlas as a system in which force, material, and movement are inseparable. Taken as a whole, the dynamics of 3i Atlas suggest emergent behavior. The object does not simply respond passively to gravitational or environmental stimuli, it acts as an integrated system, with each component — composition, structure, rotation, orbit, thermal gradients, electromagnetic fields, and microfractures — interacting continuously. Small changes in one domain propagate through the network, producing observable consequences elsewhere. A thermal microthrust affects rotation, which alters ridge orientation, modulating electromagnetic fields, which influences regolith movement, which in turn changes local mass distribution and affects orbital trajectory. The feedback is continuous, multidirectional, and non-linear. Patterns emerge from this complexity. High-density ridges serve as organizing centers for thermal and electromagnetic energy, maintaining structural stability and guiding microfracture propagation. Depressions act as buffers, absorbing stress and retaining volatiles. Rotational wobble and precession act as engines of redistribution, cycling energy through the system. Microcollisions and historical impacts leave their imprint, adding layers of complexity to an already intricate framework. Each element is neither dominant nor passive. It functions in concert with every other component, producing the coherent but dynamic behavior we observe. The integrated dynamics of 3i Atlas also highlight the limitations of conventional modelling. Standard gravitational calculations fail to account for observed drift, because they neglect thermal, electromagnetic, and structural feedbacks. Orbital predictions based solely on mass and trajectory miss the subtle but cumulative effects of thermal microthrust, Lorentz forces, and rotational torque mediated by internal heterogeneity. To accurately predict the object's future behavior, models must incorporate composition, morphology, thermal inertia, electromagnetic interactions, and microstructural mechanics, reflecting the object's systemic complexity. This synthesis emphasizes that 3i Atlas is neither ordinary nor inert. Its unique combination of surface features, compositional heterogeneity, persistent thermal gradients, electromagnetic fluctuations, rotational wobble, orbital anomalies, and microfractures sets it apart from other small bodies observed in the solar system. Each anomaly reinforces the others, creating a network of interconnected dynamics that defines the object's current state and ongoing evolution. It is not merely a collection of isolated phenomena, but a single, integrated system, operating at the intersection of physics, chemistry, and environmental interaction. Yet even in this synthesis, uncertainty remains. We cannot yet determine the full extent of subsurface heterogeneity, the precise contribution of rare compositional phases, or the long-term implications of orbital drift and microfracture propagation. Observed anomalies provide clues, but they also hint at processes hidden from current observation. Each resolved question leads to new inquiries, highlighting the limits of measurement and the potential for undiscovered dynamics within the object. This persistent ambiguity underscores both the scientific challenge and the allure of studying 3I Atlas. Ultimately, the story of 3I Atlas is one of interconnectedness. Thermal, electromagnetic, mechanical and compositional processes interact to produce a living system of anomalies, each influencing the other in subtle but measurable ways. Orbit, rotation, structure and surface evolution cannot be understood in isolation. They are emergent properties of the object as a whole. By examining these interactions, we gain insight not only into a single anomalous body, but into the broader principles governing small object dynamics in the solar system. The implications extend beyond scientific curiosity. Understanding integrated dynamics provides predictive power, informs models of minor body evolution, and may have relevance for planetary defense or future exploration. Observing how 3I Atlas responds to environmental stimuli offers a laboratory in which the coupling of thermal, mechanical, and electromagnetic forces can be studied in a natural context. Its behavior challenges assumptions, inspires new models, and illustrates the limits of traditional categorization of small bodies. As the investigation draws to a close, a clear pattern emerges. 3I Atlas is a system of interdependent processes, where anomalies are not accidental but intrinsic to its integrated behavior. Thermal hotspots, conductive ridges, orbital drift, microfractures, and compositional heterogeneity are all part of a single evolving network. Each discovery refines understanding while simultaneously revealing new questions, underscoring the object's uniqueness and complexity. In the end, 3I Atlas reminds us that even small, seemingly simple bodies can harbour extraordinary complexity. Its anomalies are the signature of a dynamic integrated system, revealing processes that challenge conventional understanding and expand the boundaries of observational science. Every ridge, fracture and thermal gradient contributes to the ongoing evolution of this small body, shaping its present and hinting at future behaviour yet to be fully understood. Even as this chapter closes, the object continues to rotate, drift and evolve. Its story is ongoing, a quiet yet profound demonstration of the subtle forces that govern small bodies in our solar system. The synthesis of anomalies reveals a system of interwoven processes, each measurable, each consequential, and each a window into the underlying mechanics of a singular remarkable object. In the silent expanses of space, 3I Atlas spins, drifts, heats and conducts, a microcosm of complex physics played out in real time. What we have observed is only the beginning. The deeper truths of its structure, dynamics and evolution remain partially hidden, awaiting further observation, measurement and analysis. And it is precisely in this tension between what is known and what remains unknown that the object's full significance lies. As our analysis draws to a close, 3I Atlas remains both illuminated and enigmatic. Every ridge, every fracture, every thermal hotspot and electromagnetic fluctuation is part of a greater system, a network of interdependent processes that govern its behaviour in ways we are only beginning to understand. Observations have revealed a body that is not inert, not passive, but dynamically alive with the interaction of heat, charge, mass and motion. We have traced its orbit, mapped its composition, monitored its electromagnetic and thermal patterns, and studied the microfractures that silently shape its surface. Each anomaly, examined alone, tells part of the story. Together, they form an integrated picture of a small body governed by complex feedback loops, where the boundaries between cause and effect are intertwined, subtle and continuously evolving. Yet, even with weeks of observation, many questions remain unanswered. The depth of subsurface heterogeneity, the full implications of compositional outliers, and the long-term influence of microthrusts and electromagnetic fluctuations on its orbit are still unknown. 3I Atlas continues to rotate, to drift, to interact with its environment, reminding us that in space, nothing is truly static and every detail can carry profound significance. In the quiet expanses beyond Earth, this small object demonstrates the intricate forces that govern minor bodies. It challenges assumptions, defies simple classification, and invites continued observation. What we have uncovered is remarkable, but it is only a part of a story that continues to unfold. 3I Atlas exists in a state of ongoing evolution, its secrets layered, interconnected, and elusive. And as we watch it, silently tracing its path through the solar system, we are left with a single, lingering thought. The universe, even in its smallest components, is a masterclass in complexity, where every anomaly, every subtle deviation, is a window into the hidden machinery of reality.